Hello and welcome. We'll get started here in just a couple of minutes. All right. Let's just finish getting set up here. And we can go ahead and dive in and get started. So hello and welcome to the final demonstration event for the OGC Disaster Pilot 2023. I see a few people are still joining, but we do have a lot to cover today. So I'll propose that we go ahead and dive in and get started. My name is Trent Tinker, and I'll be leading the webinar today with Josh Lieberman. We really appreciate you being here today and are very excited to present the results, achievements, lessons learned, and next steps from Disaster Pilot 2023. While we are presenting results here, we do want this presentation to be a discussion and encourage feedback and input as we build up to what do we need to do next. A couple of logistics before we dive in. All attendees are muted by default. Panelists are not muted by default, so any folks who are listed as panelists with all of our participants, please stay on mute. However, even though the audience is muted, we are encouraging audience participation, and there's two ways that you can participate. There is a Q&A panel that you'll see in the GoToWebinar control panel where you can ask questions to the OGC staff and the participants. We'll either answer those questions directly and share them with the entire group, or we can also, if we can't get to them from responding by text, we can also read those aloud during dedicated Q&A sessions in the agenda. The other way that you can interact is you may raise your hand if you're an attendee to be unmuted. So as we get to the Q&A session, encourage you to raise your hand and weigh in. Before we start, I do want to say a couple of thank yous. First, a very special thank you to our disaster pilot sponsors, USGS, Natural Resources Canada, and NASA. They not only provided the financial support, but also provided the ideas and the oversight throughout the project. There was also a tremendous time investment from these sponsors, as many participated in weekly meetings with the participants. I do also want to say a special thank you to our participants. Each of these participants did an amazing job working together. I think we have almost 20 participants in the disaster pilot. So tremendous effort and collaboration from them. Many of these participants also provided in-kind contributions in addition to the funding that was available. And last but certainly not least, I want to give a special thank you to Josh Lieberman. Josh not only led this pilot, but has also been a brilliant leader of the OGC disaster pilots for many years. We certainly would not be where we are today without his exceptional leadership. As many of you may know, Josh retired from OGC a couple of months ago, but has continued to support the disaster pilot up to this demonstration day today. We'll certainly miss you, Josh, moving forward at OGC, and really appreciate all of your outstanding contributions and thought leadership throughout your career to OGC. So thank you, Josh, and we wish you all the best in retirement, and really appreciate your support here today.
Thank you, Trent, very much for the kind words. And Just to let people know, I'm retired, but I'm not retiring yet. So.
All right, so with that, let's take a look at today's agenda, and it's certainly a very packed agenda. We got a tremendous amount accomplished over the past 6 months, and we've done our best to trim this down into a 4-hour presentation with some breaks and discussions built in. So after this agenda review, we'll have a quick word from our sponsors. Then I'll give an overview of OGC, our COSI program, and our pilot. After that, we'll dive into the scenarios. We'll start with the drought scenario, including a technical introduction, the participant presentations, and a Q&A session at the end of the drought scenario. After that, we'll break. Break is currently scheduled for 20 minutes. We'll certainly take a pulse and see where we are on time, but targeting 20 minutes there. And after that, we'll dive into the wildland fire scenario, followed up by the discovery and access, and the mobile survey app that can handle high volume of public responses. After that, we'll go over the provider, user, and operational capability guides, which are a very beneficial output from this initiative. And then lastly, we'll wrap up with a Q&A panel discussion where we can answer additional questions and accomplishments, and also, as I mentioned, discuss what is next. So again, a very special thank you to our sponsors. I believe we have USGS and Natural Resources on the call today, and I'd love a few words from them at this point, if you can unmute. Ryan, would you like to go first?
Sure. Thanks, Trent. Yes, so thank you, Trent, and hi, everyone. So I am Ryan Hola. I'm an environmental scientist with Natural Resources Canada, and I coordinate our various activities within the Open Geospatial Consortium, including our involvement in Disaster Pilot 2023. So our goal within the pilot was to support activities that are being led by one of our provinces in Canada, Manitoba, specifically their emergency management organization. And what they were interested in looking at is how to better connect different communities with geospatial information in the context of drought. So that's where the drought component of the project that you're going to hear about today comes from. And the rationale for them wanting to look at that was from a severe drought that the province had in 2021. And there was a realization that they didn't have significant structures in place to support all the different domain stakeholders that need access to information about drought. And particularly from a forward-looking context, with climate change coming up, it's going to become a lot more challenging, and you'll have different stakeholders involved. So we're familiar, for example, with challenges around agriculture and wildfires, in the context of drought that need access to geospatial information. But if you think broadly enough, there are many other different domains that also need access to that information. So things like the health sector, engineering, because if a drought lasts long enough, you can have impacts on things like road infrastructure, etc. So that expands, outwards, and you have to connect many different communities together. So this pilot, our goal within it was to really take a very initial first step at understanding, what does that look like? So like if I'm in the health domain, how do I access information from an agricultural community, for example, to support my own technological and decision-making needs? We're certainly interested in learning more about the solutions that were developed in the pilot and how they can inform this immediate need and what next steps we need to think about for future activities to help support Manitoba's goals in this context and also other provinces and territories across Canada. So yeah, with that, I will stop, and I just wanted to thank OGC and all the participants for their amazing efforts in this work, and we're really excited to see the outcomes of it. So thank you.
Thank you, Ryan. Rich, would you like to go next?
Good morning and good afternoon, everyone. My apologies, I will not be able to get on camera because I'm in a place where I can't do that very well, and it would probably drop my bandwidth. And just in the interest of time, I won't say too much at this point, but just really excited to see all of the participants' results. This is something that we have also been a sponsor for the past 5 years. It's a very passionate area of interest for our community, especially given the current state of disaster implications and impacts that have been happening in the global community. One of the things that we are hoping to learn from this activity is how can we take more concrete actions and leverage efficient technologies to support interoperability? And how can we then operationalize some of the great solutions that you all may present and share that within our community to help us be more resilient in the face of increasing disasters as well as extreme climate. So thank you so much and I'll reserve some of my comments, Trent, for the final discussion.
Thank you, Rich.
Flood and climate.
All right, and just as a double check, do we have anybody on from NASA who would like to speak? If you are an attendee, you can raise your hand and we can unmute you. I'll give you just a minute, and otherwise we can continue on. All right. So now I'd like to give a quick overview of OGC and where the disaster pilot sits within OGC. So OGC has two main groups: our standards program, which you see on the right-hand side here, which is our traditional approach for developing standards, and our collaborative solutions and innovation program, our COSI program, which does rapid prototyping, runs tests, provides engineering services, runs pilots such as the disaster pilot. So both of these programs, of course, work very closely together, as you see in the diagram there. For example, the COSI program, it may take new or evolving standards and apply those to real-world problems like disaster response, for example. And also through the COSI program, whether it's exploratory stage in our test beds or in a pilot where we may identify a new interoperability gap, sometimes the COSI program can feed some of those requirements, or even in some cases with test beds, draft standards into the standards program as well. So as a result of the process that you see here on the screen, OGC is accelerating standards at the pace of innovation driven by purpose. Taking a closer look at the COSI program, here you see the types of projects we run and roughly where they sit from a TRL perspective. Within the COSI program, we do experiment with new technologies, test emerging and existing standards, demonstrate their capabilities in the context of real-world challenges that are defined by the user community. It's worth pointing out that although traditionally COSI initiatives fall more on that R&D and exploratory side, we are starting to see more and more participants' deliverables move into that operational capability. We've also had a focus recently on ensuring that the capabilities that are created in an initiative can be usable and demonstratable beyond the life of this pilot through a persistent demonstrator. So what goes into a pilot like the disaster pilot? Well, the short answer is a lot. It's a lot of coordination and collaboration, and I can try to walk you through that a little bit here today. So it all starts with a use case and a challenge, and this challenge is often shared across multiple sponsors, which is really beneficial as funding resources and requirements and needs can all be pooled together. Next, you have the people. Certainly, you have, of course, the sponsors who tend to be our strategic OGC members. There's also our global consortium of geospatial experts, these OGC members who can respond to the initiative, receive funding, and execute the work. As I say that, I do want to point out that you do not have to be an OGC member to respond to a call for participation. So in the future, if you are interested in presenting or participating and you're not an OGC member, please still go ahead and respond. Throughout an initiative, we also coordinate with stakeholders, whether it's in-person workshops or virtual meetings. And then output from a pilot can include things like an engineering report, persistent demonstrator, as I mentioned, user guides, as you'll see today, and then, as I mentioned, also feedback into the standards program and much more. So what was the focus of DP23? We'll certainly get step by step even more into the details here, but I can start out with a high level overview. So within the context of disasters, we are focused on data to decision workflows. So think about going from analysis ready data to decision ready indicators. We focused on flexible and scalable workflows for decision makers, publication of user guides, and immersive visualization. The two scenarios that we looked at here were drought and drought impacts in Manitoba and wildland fires in the Western US. So within the initiative, we have several technical components. These included the data to decision workflows, the decision ready indicators, the decision support tools, volunteered and crowdsourced observation capabilities, and also shared perspective through, for example, the immersive visualization. There are also resources that are available as an outcome of the disaster pilot. One of our sessions will be focused on the guides that are available. And I also do want to point out, as you see here on the right, there will also be a publicly available engineering report that is published. So after today's presentation, if you want to dig into any of the details on a particular scenario or a particular deliverable, the engineering report is going to be the place to do this. These reports are published publicly on our OGC website after they are approved with an associated OGC domain working group. So please stay tuned with the engineering report, and certainly can check out a lot of our past work if you search for engineering reports on the OGC website. So today we're going to give a really excellent presentation of all the work, the progress, and the collaboration that's happened during the disaster pilot. As you listen to the presentations, I really encourage you to not just think about what was accomplished, but also think about what is next. What are the next items that are critical? What's most needed? Where are the interoperability gaps still? How do we make even better use of the data and the analytics that are available to improve decision making? As a follow-on to this pilot and the successes of this disaster pilot and also the climate resilience pilot, OGC plans to combine these two initiatives into a climate and disaster resilience pilot 2024. So that's kind of the next step or the next phase of the disaster pilot. So the climate and disaster resilience pilot will consist of a couple of individual threads, which will each work towards specific end user, stakeholder, and technical goals that advance our climate and disaster understanding and readiness, while also seeking collaboration between these two domains. So we expect the call for participation for this phase, for this first phase of the next pilot to go out later this month. So please keep an eye on that if you'd like to participate. And then we also anticipate a second phase that'll take place in the spring as well. Additionally, we have an in-person event coming up quickly here, December 5th through the 7th. That's going to be in Washington, D.C. at the American Red Cross headquarters. So please visit our OGC events webpage to learn more about this event, take a look at the agenda and the speakers. As shown here, former FEMA Administrator Craig Fugate will give a keynote presentation on the first day. We have some excellent panels lined up, and then the second day we'll have some really good industry demonstrations of geospatial in action to address climate and disaster resilience. So in many ways, this Innovation Days events is a continuation of the discussions here today with an in-person event. So with that, I'd like to hand it over to Josh, and I will do a transition here to dive into the drought scenario.
Great. Let's see. Do we have camera? There we go. All right. And hopefully you can see my slides.
Not yet, but I will show them here. Oh, you're showing them. All right. Yes, perfect.
Cool. All right. Yeah. Thanks so much, Trent, for introducing the session, for leading and facilitating the pilot. And it's made it much easier to move on to some later phases, later acts of my life, knowing that this important work is in good hands of yourself and other members of the COSI staff who are carrying on this and other initiatives and really accomplishing important work and collaborations in that context. So what I wanted to do was to put the work that our participants are going to talk about and demonstrate here in a little bit more of a context of why did we do this? Why do pilots need scenarios? And the reason is that, you know, this is intended to behave like reality, right? We want a good ability to test new ideas and new standards and ways of solving data sharing challenges and have better outcomes because of that. But we need a balance between that and limiting the risk and expense of doing that. So not diving into an enormous operational capability before we have knowledge and experience about what works, what doesn't work, and what the pitfalls, but also what are the requirements? What do people need to do? So OGC pilots utilize one or more scenarios that they combine selected sharing challenges, standards-based solutions, and look at limited but representative, and this is the critical part, times, places, and stakeholders. So this addresses a set of challenges which are specific to this pilot, but that we occur again and again. And it's why we carry out these pilots, so that we can continue to figure out how to address these challenges. An enduring challenge, of course, is access to the right data for implementing a realistic scenario, despite privacy concerns, propriety concerns, cost and scale, lack of analysis readiness, you know, the processing that's involved. And these are specific to the pilot, but they are the challenges that we run into when actually trying to get these capabilities out into the world and into operation. So we need to solve them in the pilot so that we have a path to solution when people actually go about this. And we know from the feedback and discussions and collaborations we have that we run into exactly these same problems in trying to operationalize and save people in real situations. So we need to solve them now. The more specific challenge to a pilot is actually engaging with representative stakeholders. So some of this is people like first responders who are very busy and have limited time to do this kind of experimentation. But it turns out in many cases, those stakeholders are not being involved in the operational situations either, that they lack information, that they lack give and take, that they lack the awareness that they really need to do their best work. The gist of the challenge is, can we get the right information to the right person at the right time, in the right place, in order to guide the right decisions, the decisions that actually need to be made, and thereby lead to the best outcomes possible in these difficult situations. Now, Since this is an OGC pilot, there's also a challenge to utilize, critique, and improve OGC standards, the standards-based approach to data sharing, which is the OGC mission. However, this is not so separated from the beneficial outcomes that we're seeking as well. And this is a expression that I've always appreciated from David Schell, who the founder and chairman of OGC, which is we sneak in with discussing interoperability and the information and the technical details, but really what we're trying to do is to get organizations to work better together by providing them the tools to do so. But we try never to lose sight of that's what we're really trying to do, is to make organizations work better together for people. We have a paradigm that allows this collaborative geospatial, place and time-based collaboration in urgent situations, and that's this, emergency mapping, emergency operations center. Everybody gets together in person, they bounce ideas and information against each other and come up with a common way forward that is very responsive to changing situations. This is great, except this is very difficult to do, particularly in ongoing disaster management. Having people sitting in the room forever is just not feasible. So how can we take this paradigm and translate it into a digital, online, distributed, and persistent paradigm? And that's where the workflows and the collaborative means that our participants have been piloting, that's where these come in. In particular, in emergency and disaster management, there are these very important principles that all of our work have been aiming towards: the inclusion of all potential players, the real human contact, whether it's in person or online or through these mediating interfaces. How do we make that contact work so that we can develop mutual recognition and respect, and particularly sincerity, so that there's trust and ability to act on the information that we share with each other, and particularly problems of unintentional insincerity, such as people preferring to work with others like themselves and having difficulty extending the community of stakeholders as needed to actually have beneficial outcomes. So that's what we're working towards. And this sort of data to action value chain that Trent introduced is really what the workflows developed by our participants is aiming towards. How do we get from the amazing data sources that we have available to us to the public, to other stakeholders, actually being able to take good decisions? And so that's what we're aiming towards. And most particularly, the workflows that you'll hear about are about exemplars. Given all the sources of information that could be involved and all of the people, situations, decisions that need to be made, there's a very broad possibility of these recipes for decision-ready indicators that could be developed. What we try to do in the pilot is to present templates, to present exemplars of how this could be differentiated and specialized for the exact decisions that evolve over time in these situations. So, drought. Why did we focus on drought as one of the hazards and scenarios in this pilot? We've worked on many other hazards in the past, from 2019, 2020, 2021, and so on, to get to 2023 here. We've worked on floods, landslides, pandemics, storms, all sorts of hazards, but drought is different. It's particularly different in the sense of the time scale that drought occurs over, that action needs to be taken, that awareness needs to be developed, weeks to years. In fact, drought has this interesting positioning between extremely immediate disasters and the slowly developing frog boiling situation that we have with climate and climate change. And so it occupies a unique position as one of the manifestations of climate change that connects these slow changes, in some cases not so slow, to these most immediate occurrences. So it's a complex mixture, a complication and cascade of these impacts. So the direct ones, uptown just lost their drinking water, lost the crops because of loss of irrigation water. Indirect effects, health effects of toxic dust thrown into the atmosphere, and then the indirect effects which are on their own timescales, and that is geographically intricate. One well runs dry, the next one continues to draw water. Who needs to do what when? Paradoxical, heavy rains and storms that still, because stormwater practice was to get rid of that water as soon as possible, they're not then participating as they need to in the hydrologic storage that relieves droughts. So that paradoxical nature is very confusing in terms of particularly public awareness of where we are with this hazard. And of course, the role in the disaster ecosystem, I'll call, the complications and cascades. For example, drought produces fuel that leads to wildland fires, bearing slopes that then slide in flood conditions. It's a part of this constellation of hazards that we need 24/7, every day, every year, need to be aware of, to work on, so that we develop the disaster resilience, which blends increasingly into climate resilience. Hence the combining of viewpoints that will be a feature of the work in disasters with OGC and members and partners as we go forward. So without further ado, let me turn to the participants' work in developing these indicators, which are exemplars of how to work with drought, particularly in the area of the province of Manitoba, but with much more general implications. Pixelytics, SAFE, will work on the indicators of drought severity. 52 North will talk about crop impact indicators. RSS Hydro will present the impacts on water supply. HSR and IIT Bombay will talk about health impacts, and GECO Sistema will work on energy impacts. Hopefully we'll have a little time for the key takeaway from this work, and as Trent indicated, we really want to focus on the next steps, both in disseminating what we've learned and figuring out what the next challenges are. So with that, I'll turn things back to Trent to go on to the participants.
Thank you, Josh. All right.
As you're switching over, can you hear me okay?
We can, yes.
Excellent. Okay, so if you can make me presenter.
Yes. All right. You should be presenter now, Dean.
Okay, excellent. And my audio is still fine? Had a little mic trouble before. Excellent. Okay, I'll jump right into it. I just wanted to thank Josh and Trent for kind of setting the stage, and also the sponsors here, Rich and Ryan, for making all this possible. And so I'm going to talk briefly. I'll introduce things and then hand it off to Sarah and Sam. So I'm Dean Hintz from Safe Software, and we're working with Pixelytics and University of PEI on this drought indicator. So basically, our goal here is to assess current and future drought risk. And basically what we do is provide inputs related to transforming climate model data so that the Pixelytics drought model can model future, and they also have a lot of sophisticated modeling that take into account past and current data to feed the drought model. And then Sarah will talk a little bit more broadly about what's important to consider and how to engage with stakeholders and citizens when developing impacts and indicators related to drought. So just quickly on the Manitoba context, as Josh introduced, specifically, you can see from the Canadian and Manitoba Drought Monitor some sample dashboards. Drought is a key factor, obviously, in food security, as well as fire, health, environment, and economy. And in Manitoba, that would also include hydropower. Historically, it's been more of an issue in the Western prairies, but with climate change, it's become much more evident in recent droughts here in southern Manitoba. So basically, our main objectives here to support a drought indicator is Sam's work around containerizing the drought model and exposing it behind OGC services to make automation easier, focusing not just on vulnerability or impacts, but also on vulnerabilities. And from our side, building ARD to support the DRI and provide a future perspective, because the past is no longer a useful predictor of the future given climate change trends. So in terms of our contribution, we basically sourced climate data for southern Manitoba and then used our FME platform, spatial ETL techniques to simplify that data and make it easier to use and interact with for impact analysis. And the real focus there is taking what typically are global climate model data and sort of looking at that in the local context and making that all available via web services and open standards. And in terms of the data sources we used, Environment and Climate Change Canada has a data portal for statistically downscaled climate scenarios, and we chose the business as usual RCP 4.5 for that. And basically what you get out of that is the data cube that you see on the right, where you have this fairly complex, it's difficult to access from a GIS perspective, this time series of environmental variables. And so how can we make that more accessible to a wider audience? That's kind of zooming in a bit more on what the data cube looks like from FME Inspector, Data Inspector. And so basically for the ARD that we derive from that, we explode out that data cube and convert the raster to vector, load that into a spatial database, and then feed a OGC features API based on that. And so this is just a little more detail about the workflow for configuring the data cube to those time series points, and then serving that up via OGC API. And so this is just a simple query that models drought, and we can of course improve on this, but this is one question we tried to answer. What areas of Manitoba in the next 40 years are going to be 25% drier than the historical mean and monthly temperature greater than 23°C? And so this is just some of the raster algebra that we did to do the precipitation delta, which is the normalized value from 0 to n, where 1 is the same as the historic mean. And that's the answer. So we found there's just a small set of points south of Winnipeg, just in 2048 and 2058, that actually met that condition. So out of a couple of million input points, only those 60 odd satisfied that condition. And so that might be an area to focus on further study. But so for more on that, I'll hand it over to Pixelytics.
Yeah, thank you, Dean. And next slide.
Okay.
So our part in this activity was to take an existing algorithm, which was the Sepulcher and Canto approach, which is a combined drought indicator encompassing precipitation, soil moisture, and vegetation, and containerize that so that it could be pulled and used by anyone. We picked that particular algorithm as it's already being used by Copernicus as a drought indicator, and the aim of this work wasn't to develop something new from a scientific perspective. Instead, we were looking at developing something that was flexible, scalable, and resistant in terms of a workflow. So we built a front end that is a OGC web processing service where the user calls the drought indicator by specifying a box, and then the back-end processing pulls in the data sets it needs, which can be Copernicus or NOAA, and then provides that data back to the user. And the plots being shown here show that indicator coming back, and as the colors scale from yellow to orange to red, you're looking at giving someone a warning to an alert that drought is occurring as you proceed through those parameters. Next slide, Dean. And so this is what it looks like when a user pulls that workflow. So in order to make it as simple as possible, we've taken an existing QGIS plugin, and you can call that indicator from that plugin, and it will give you the output. Also, what we tested with Dean's web server from Safe Software was not only pulling in the historical data sets, but also future scenarios, so that you can look at drought historically plus into the future as well. Thank you.
Okay, over to Sarah.
Well, thank you, Dean and Sam. My work was focusing and built on over the explanations that essentially Ryan and Josh provided. I looked at and worked before with the province of Manitoba through Ryan, and I know their problem with the drought severity, and given that there is a federal level Canadian drought monitor, the main question was how we can develop that into more interoperable and also vulnerability assessment tool. So I worked on presenting the requirements for drought impact and vulnerability assessment, and also investigating the current condition of Canada and drought monitor programs, and providing suggestions on how to achieve timely disaster response requirements. Additionally, in my new group, we are going ahead with working with that kind of setup for the drought monitoring system to include citizen science and other stakeholders to this, and see as a pilot how we can achieve that, given that Prince Edward Island is the smallest province. I'm hoping that we can achieve such a tool as a demo, and then expand it to the federal level. So I presented this work with looking at the mostly the U.S. National Drought Mitigation Center report, and here I give you a brief summary of that. Next slide, please. So the one point of this work was that drought impact assessment is always different from vulnerability assessment. Impact assessment is to understand what are drought causing in an area, and this can be different for every region. For example, in the case of Manitoba, the biggest economic or direct impact is on Manitoba hydro exports, or farming and cattle raising and related companies, as well as wildfire fighting. This can also be translated into environmental and social impacts, but and a lot of them are basically interconnected. But it's important to separate them in every case to see what are different cases of drought that can cause because when we come to tackling the drought issues, it's important to have priorities because not that all issues don't matter, but given the budget and time, we might have to prioritize certain issues in a certain region to tackle that. And then we also have to identify which of these impacts are based on recurring droughts or based on very long-term drought, or which of them are supposed to come back more often, and prioritize it based on that. So next slide, please. Yeah, and as we prioritize them, we, for example, come up with the first 3 important ones that are worth investing and bringing the different groups of people, combination of people from different backgrounds to feed into that problem in order to solve the issue. So this brings us to the vulnerability assessment, which is looking for whys, because drought can hit different regions in the world, but doesn't necessarily cause the same damages in different areas. For example, if we prioritize that income loss due to crop failure in the area is important to be addressed, the next step is that we have to understand why this crop loss is happening, and there are different reasons, and we have to list them and then find possible actions that are relevant to that. For example, this can be due to because of having no drought warning, which is why, for example, drought monitoring systems are there, but then it can be also because of the fact that the farmer is reluctant to use, for example, drought-resistant seed, or they don't believe that this is a good solution, or they don't like to do irrigation. So each of them needs to have possible actions. So some of the main points of this work was, first of all, the importance of working not only on the impact, but also the vulnerability, not only looking at what's, but also why's. The other one is, the other point that I wanted to make with this was the importance of bringing the right mix of people with different backgrounds and the citizen science also, in order to transform drought monitoring tools to an interoperable system. And last point that I made was that drought disaster responses in that sense might be more suitable in a regional analysis rather than a global effort. For example, there are UN efforts in terms of addressing drought issues in a global scale, which I think might be less effective when we are thinking about future connections with the stakeholders and different categories of people. So it's better to tackle it in every region depending on the needs of that region. Thank you.
Yeah, if you guys can hear me, I guess we better wrap this up because we're out of time. So I think
yes,
Sarah highlighted. Yeah, Sarah highlighted her, did a great job of summarizing issues around assessing vulnerability, not just impacts. Sam gave some great examples of how her drought model is containerized and interoperable, which supports automation. And our main focus was giving direct access for the users to the climate model results. I think I'll just make the last point that user interaction with indicators in the local context that Sarah just talked about is key to improving disaster manager and stakeholder understanding of the impacts, and also for providers to improve their synthesis and simplification and presentation when we get feedback from stakeholders. So you can look at what's next when you get the deck. But Sam, did you want to highlight anything else, or should we just wrap it up?
I think we've probably run out of time.
Yeah, okay. So I think the last point I'll say is we really need a synthesis of past, current, and future data to give a real sense of what's going on with the trends, and at least we've taken a first attempt at that. And yeah, the past is no longer a sufficient predictor of the future, and so we're working to address that. Thank you.
Perfect, thank you. And we will have some time for more comments during the Q&A session. So I'm going to unmute 52 North, who is going next. So you should be able to hopefully speak now.
Yes, hi, can you hear me all right?
Yes, we can. And I will make
Perfect.
myself presenter to share your slides here. Okay. Okay, the floor is yours.
All right, thanks a lot. Yeah, hello from my side. My name is Katharina Demmich. I'm a research software engineer at 52 North, and today I'm here together with my colleague Johannes Schnell. And 52 North has been implementing a workflow for visualizing the impact of droughts on crop health and production. Next slide, please. Yeah, I guess we all know that due to climate change, we have an increasing probability for extended drought periods. And one sector that is heavily affected by drought periods is, of course, the agricultural sector. And if we look, for example, at the drought that happened 2021 in Manitoba, then on the right side of the slide, you can see the drought monitor for July, I think, 2021. There have been large areas in Manitoba have been affected by severe droughts, extreme droughts, and even very extreme droughts. This led to a loss of roughly 20% reduction in major crop yields, and also a total direct loss of about $75 million. And if this is only the sum that you calculate, if you do not consider that at the same time also the crop prices have been increasing. So if you correct for that, you reach a number of roughly 1 billion actually. Because of this, it's of course very important and also interesting to investigate how environmental conditions can affect crop production and crop health. And in particular, if we can pass decision-ready data to farmers, then this can enable them to much better adapt to drought impacts. Next slide, please. This is why 5N for the disaster pilot has implemented an OGC API processes that provide so-called crop suitability maps. We've been working also in the model region Manitoba, and the model that we have been using for that is a very simple one that takes the forecast data for precipitation and temperature for the upcoming month and compares it to plant requirements. The data that we have been using for this is from the Meteorological Service of Canada. It's the monthly forecast for precipitation and temperature, and in more detail, we're using the Global Ensemble Prediction System. The plant requirements we take from the so-called EcoProp database of the Food and Agriculture Organization of the United Nations. And on the right, you can see some of the tools that we have been using for the implementation. So the OGC API processes has been implemented using Pageo API. Everything is installed in a Docker container, and we deployed it in an Open Telecom cloud. If you're interested in looking at that application, you can either go to the link at the bottom or you can scan the QR code here on the slide. Next slide, please. Yeah, some more words on the output of this tool. So as I said, the tool provides crop suitability maps. These are maps where regions are highlighted in different colors according to how suitable the environmental conditions in this region are for crop health. We differ between 5 categories here, reaching from optimal to pessimal. And we can provide results either for a particular bounding box, so for a particular area, or just for a single coordinate pair. The output format that is provided is either GeoJSON or a netcdf file. For GeoJSON, you can see an example on the top right. Their regions with different with the same suitability are combined in polygons. And on the top right, you can see an example for an SCDF file where the different categories are provided as variables. Yeah, both of these formats can easily be integrated in any geoinformation system, and they can easily also be visualized using tools like QGIS or GeoJSON.io. And with this, I would like to show a short demonstration.
I'm going to transition to the video here. It may mute you. If it does, I will unmute you.
Mm-hmm. All right, I think I can still talk. My mic is unmuted. As I said, I want to show a short demonstration. You can here see the landing page of the API processes that we implemented, and we have a look at the API documentation. If you scroll here down to the endpoint crop model execution, then you can now see the parameters that needs to be passed to the tool. These are either the bounding box or a particular coordinate pair, the crop species, and the output format that you like. And if this request is executed, then in this case, since we ask for GeoJSON, you also receive a GeoJSON file where you can see the output right here. And if you store this and visualize it as it is done here with QGIS, then you see the crop suitability maps for the model region of Manitoba, with different suitability categories displayed here from green to red with decreasing crop suitability. And since we have the EcoCrop database connected, we have access to about 2,000 different plant species. And we can not only pass a bounding box, as I said, but also just coordinate pairs. This can, for example, be visualized using GeoJSON.io. You can here click on the individual points, and the suitability category is displayed as well as the crop species that you're looking at. And with this, I would like to go back to the presentation, to the achievements. Yes, so quickly summarizing, what we implemented is a tool to visualize how the environmental conditions impact the well-being of different crop species. You can also again see an example of a map here on the right for maize in August 2023 that has been produced with the model. And yeah, with this data, we hope to support farmers to really adjust to drought conditions. So for example, adjust their irrigation schedules or just choose a suitable crop species that is more adapted to drought periods. Yeah, 5-N is not only participating in the disaster pilot, of course, but we're also participating in two projects which are funded by the European Union and which are a bit similar. That's the ISISC and the Directorate project, looking at web services for climate change adaptation and disaster risk management. And the tool that has been developed for the disaster pilot also serves as valuable input for these two projects. Then there's several refinements that can still be done to this tool. So right now we are still using example data. And of course, it would be nice to automatize this. We are not providing any modeling uncertainties yet. So that would be, I guess, a good thing also to interpret the results. And yeah, it would also be nice, I guess, to have functionality to compare the suitability for different crop species. Then you can go to the next slide. And I thank you for your attention. If you like to have a look at the tool, you can scan the QR code. And then on the next slide, yeah, maybe we can just quickly flash the references. But that's it then from my side. Thank you.
Thank you for that presentation from 5-N. Next, we have up the water impact from RSS Hydro.
Hey, you should all see me now. Sorry about the light. It's a bit odd on the screen. Yeah, if you could bring up the slides, that'd be great.
Okay.
Please, thank you. Yeah, so thank you for having me today. I mean, it's a pleasure to be here with you all, and there's been so many things being said already. So I think I can skip a couple of slides in my talk on the intro. But I'm here, Guy Schumann. I'm here to present the D103 water availability or water impact on droughts, and I'm with Arsus Hydro, a company out of Europe doing R&D in geospatial innovation. So we have been with OGC for quite a while on these testbeds, and it's been always a pleasure to be here. I also want to thank the sponsors, USGS, Natural Resources Canada, and NASA for this. And we as a company are very carefully, investigating whether we can address or help address the SDGs related to water risks, and it's very much in this pilot that we actually participated to do that, to showcase our data. But we do that in collaboration with a lot of partners, among others the Flood Observatory here in Colorado Boulder. We're working with Albert together and using his passive microwave data. So I'm going to show you in a while what that is. And next slide, please. So this has been said before, and we saw that image on Josh's presentation. I mean, it's unfortunately an image that is not pretty at all, but it highlights very well the issue of water availability, water supply, water for irrigation, and what happens if a big drought hits. And that's exactly what unfortunately happens in Manitoba in 2021. And it's also a region in Canada that is often hit by floods. So it was really devastating agricultural production that year, because there was also locust swarms then feeding on what's left in the fields, and so it's really devastating for agriculture. And I think a lot of these fields won't be coming back to production soon, so monitoring water availability daily and at basin scale is becoming more important than ever. And because of climate change, these situations are very important for looking at global food security, as I think one of the major problems we are facing and will be facing. Next slide, please. So Josh has also mentioned this, but I tried to put it a bit in context of why I use it here. It's how to move from analysis-ready data that now a lot of satellites are providing and a lot of other data producers are providing. So they put all their observations already in what is called ARD, or analysis-ready data, or cloud-optimized data. So there is now no shortage of data anymore that can be used for learning about insights on things, and in earth science is what we need to understand to make it all a better, sustainable future. And so what we are lacking a bit is how to turn that information content into actually decision-ready indicators. And that is really not possible without the stakeholder in the loop, I think, and so does OGC and all the participants that are here, because actually in 2021, the disaster pilot back then looked at actually at this value chain, how to move from the data we so often see, making it into useful information and putting that information into decision support systems that actually are, I don't like the word non-expert, that actually experts on decision making can use, but maybe not understanding the complete science behind the data or the models, but actually also shouldn't care too much about that, because that's not the part of their job. But what is their job is to make a decision, and that decision can nowadays be informed by great data. So it just needs to move to this, what we call decision-ready indicators. And next slide. So in our activity here, we use that decision-ready indicator, but link it to water availability. So, and to do that, we work with the Water Science and Watershed Management branch of Manitoba, and they are interested to see if there's a sub-daily data feed that can be put into their platform, management platform, that can actually tell them, what is the variations of water availability in a given basin or sub-basin, or if you like, a smaller watershed or water area. So the thing we need to work on is, we need a directed data to decision workflow. So it has to be instantly deployable, adaptable, and scalable. So it's all these great words, but it actually needs to go from ARD, as I showed you before, into decision. And the decision-ready indicators then is really to what I just said, to inform them about sub-basin scale, water variation, So, and there needs to be some shared perspective. So we need to understand how to visualize that data, how to communicate that indicator into maybe using a visualization environment that maybe the end user already has in place that can be shared with practitioners. Next slide, please. So I tried to make the next slide a bit less technical. This is, of course, the technology we use or is used at University of Colorado Boulder to look at water availability all around the globe in certain areas in watersheds. So we use something called passive microwave. So this is basically a sensor on board satellites. And the best known constellation here is the Global Precipitation Mission constellation of satellites. It's a joint effort between US, Japan, France, India, and other countries in Europe, especially ESA. And it's looking at, you know, a bunch of instruments on these satellites. And one of those is passive microwave. So it's recording the emitted energy from Earth that is related to the microwave spectrum. And this is very, very, very sensitive to water variations. Let it, you know, maybe groundwater, groundwater not so much because it's too deep, but it's looking at surface water, soil moisture, it's looking at rivers, it's looking at everything that is to do with changes in water on the surface or very close to the surface. So using approximately 25 years of those satellite technologies and sub-daily or daily records, at least daily, but now sub-daily records, we can actually start looking at water availability, whether it increases or decreases over specific intervals in time. So that's week, month, or seasons, or even years, for given what they call water watch areas. So we calibrate that satellite signal over certain areas and look for water variations. And this tells us a lot about water availability. And if we monitor that at sub-daily scale, we can actually derive a DRI that can inform the decision makers on what actions they may be taking. So defining those actions, that's of course up to them or other specialists, that's not us. We're providing a direct stream of the analysis ready data to the decision ready indicator, which is water availability. So, and then this availability variations of water can be linked, of course, with temperature and precip. So we can look at what effect the climate or the weather has on that availability. And because we can do that, we can then also bring in the climate models Dean was mentioning before. We can start correlating these long trends in observations from satellites and give it a kind of predictive capability. Next slide, please. So that's what's in the box technologically. And then this is one example of what the data actually looks like. So it's a huge time series of 25 years of records that we have been doing. And so we can derive statistics from it. So the green line you see is what we call the hydrological base flow of a subbasin or an area. Could be a river, could be a smaller watershed. And if the black line, that is the daily variations of water, if that falls below the green line, we're in trouble for a long drought. If it consistency, you know, if that consistently stays, it's a prolonged drought. And if we move into the upper thresholds of these horizontal red lines, we're looking for flood. So both extremes can be monitored. Next slide, please. So, and I think that's my second to last slide. So that's an image to show you that this can be done globally, and we color it in by colors looking at either flood or drought affected watersheds globally. And it's updated sub-daily, so twice a day at the moment. And this is really close to the best in real time we can do. Next slide, please. And so this is the last slide, actually, sorry if I run a bit over. We continue to implement that DRI into the Water Science and Management Board, branch of Manitoba, and we make it more relevant to decision support disaster management in that by doing so. We need to, of course, further still improve the accuracy of the technology, which we capture these availability status in rivers and wider watersheds, and we're thinking about using also ML AI technology to get there, to get rid of that signal error we see sometimes more or less in places. And then we want to correlate that measurement, as I alluded to before, with current and future climate change impacts. And just to give you another hint of how important that is, only 0.5% of water on Earth is available fresh water. We all know that. But what some of you may not know is that over the past 20 years, so exactly the same time period we've been monitoring with satellites the water availability, the terrestrial water storage has dropped at a rate of 1 centimeter per year. And of course, then it becomes very clear what that means for global water security issues, according to WMO. So I hope this has illustrated to you that it is very important to monitor this and get it into decision-ready indicator that can be used by decision making. But I stop here and thank you all very much. If there are questions, our emails were on the first slide. Don't hesitate to email, or I'm staying on for later for the Q&A. Thank you.
Thank you. All right. And next up, we have HSR Health with the health impact, and we'll have IIT Bombay with health impact as well. So Paul, would you like me to pull up your slides, or will you be presenting those?
For this drought scenario, we'll just be playing the demonstration video.
Okay.
Drought is a unique disaster that covers large areas of the world and can persist for long periods of time. Identifying where resources and personnel need to be sent within the affected areas to help the local population is a core part of the disaster response and relief effort. To address this need, HSR Health has developed, through the support of the Open Geospatial Consortium's 2023 Disasters Pilot and pilot sponsors Natural Resources Canada, our Drought Health Risk Index, which has been tailored for Manitoba, Canada. The vulnerable populations and health impacts from drought are broad and far-reaching, and only exacerbated in severity the longer a drought lasts. Some of the impacts include increased prevalence of disease, heat stress, dehydration, malnutrition, and impacts on mental health. The Drought Health Risk Index identifies a priori the health and medical needs of the impacted population and informs emergency response personnel, public health officials, governments, economic development, city and civic planners, and global public health organizations the information that they need to develop policies for resilience during a drought to limit its impact, as well as speed response and supply efforts during a drought scenario. Shown here is a dashboard built in the ArcGIS Online environment of the Drought Health Risk Index for Manitoba, overlaid with drought severity from the North American Drought Monitor that indicates the regions of relatively higher health impacts from droughts and where resources may be more at need. The underlying health and social data of the population is included in the dashboard and associated layer, a subset of which is shown in the highlighted table. The Drought Health Risk Index can be combined with other indicators such as the Drought Severity Indicator from Pixelytics that offers additional information on the severity of drought in Manitoba. We utilize the NAPSIG symbology for the Drought Health Risk Index, which was recommended for layers pertaining to disaster response based off of input from FEMA. The Drought Health Risk Index is calculated through a weighted combination of the health and social characteristics of the impacted population. The populations at greater risk of adverse health outcomes during and after a drought include the elderly, those with difficulty with mobility, and those requiring regularly scheduled care such as dialysis. The data for these factors was sourced from Statistics Canada, the Canadian Chronic Disease Surveillance System, the North American Drought Monitor, and Pixelytics. The primary standards utilized for the Drought Health Risk Index include WMS, WFS, OGC Features API, ISO 3116-2, GeoJSON, and GeoParquet. During this pilot, we began researching standards relevant to the data utilized, including ISO 3116-2, ISO TC 215 Health Informatics, and HL7. Future pilot efforts should continue to explore standards relating to health and demographic data and data exchange. The Drought Health Risk Index is published on HSR Health's OpenGeoMD platform, which is deployed in the AWS cloud through both an Esri ArcGIS Enterprise stack and a GeoNode and GeoServer open source stack, as well as made available through other catalogs in the pilot. When viewing each layer for the Drought Health Risk Index in the OpenGeoMD platform, users can import the layer into their own system through a WMS GET request via a link in the top right. Additionally, the data is made available through an OGC API instance as shown here. The Drought Health Risk Index will remain available on the OpenGeoMD platform as a persistent demonstrator. To expand upon the capabilities of the Health Risk Index, it will be incorporated into our generative AI-based GeoAI for Public Health platform that utilizes decision support and generative AIs based on large language models to provide supplementary information and real-time guidance to emergency response personnel to aid in responding to the impacted populations. In future climate and disaster-related OGC pilots, the capabilities of the indicator can be expanded through incorporating climate models and synthetic population modeling to predict the health impacts and severity of future droughts in Manitoba. Additionally, we can demonstrate interoperability through ingesting the outputs from the fellow participants in this disasters pilot to enhance the capabilities of the Drought Health Risk Index. Thank you very much for watching this demo. For additional information, please visit our website or contact us at impact@hsr.health.
Thank you very much, everyone. I hope you all enjoyed our demonstration video for our contribution to the drought component of this disasters pilot. I would like to now turn it over to Sumit for the presentation of his component. Thank you very much for your time.
Thank you, Paul.
Thanks, Paul. Okay, my slide's up. Hello, I'm Sumit Sen from GIC Hub, IIT Bombay. We are very excited to be part of the Disaster Pilot 2023, and thank you for having us here today. We have worked a bit on the health indicators for decision-ready information in the context of droughts. Can you go to the next slide, please? Next slide, please. Okay. As we heard from some of the other participants, droughts have been have a major impact on health. Some of the effects are direct, some slightly indirect, but nevertheless, all these need to be measured and controlled. Our efforts in climate resilience should be looked carefully by monitoring these indicators, and many of them are already in place as part of SDG indicators. It is important that it becomes increasingly difficult to measure and control these variables at different levels of granularity, especially that we know that there are flow of people and goods and capital and information. So while long-term aspects of the drought naturally overlap with other factors of human society, including economic development and institutional support, we started working on some of the recipes for the disaster pilot in terms of the health impacts on drought. Can we go to the next slide, please? Next slide, please. Yeah, so we looked carefully to the direct and the indirect indicators of health impacts in the context of the journey from data to information, more specifically from analysis-ready data to decision-ready information. We see that multiple sources of data, both primary and secondary, is processed and served as APIs. Spatiotemporal and spatial and spatiotemporal aggregation is applied to ensure dashboards can mix and combine information. I have to mention that our work is focused on drought data in India right now, not related to the Manitoba use case, but we can easily extend this to many parts of the world. So we should look at our work in the more general perspective of the overall inputs for policy making and for the decision maker. Next slide, please. Next slide, please. Okay. Yeah, so here is the overall view of how indicators come through. So there are multiple sources of data such as those related to meteorological scenario, vegetation scenario, and so on, leading to water shortage, increased food prices due to non-availability of local foods, and so on. These lead to direct effects such as nutrition-related effects, anemia, wasting, stunted growth, especially among children, and in the context of pregnant women. Airborne effects on health in drought areas are being monitored in many parts, especially over time effects among vulnerable sections such as children and old people. Of course, water, sanitation, hygiene related effects in the situation of droughts are also very critical and are being monitored. Mental disorders are also a major effect of drought, especially anxiety and even suicides. So chronic dehydration have major impacts in the organs of people living in communities that are facing droughts. At the same time, there are direct effects such as dehydration and related morbidity and mortalities. Hunger-related direct effects and deaths are also, they are not as common as it was decades ago, thanks to better goods and information flows, but they are not totally gone. So we know heat wave deaths from hypothermia have been counting up in recent times. Looking at these numbers in the context of infants and elderly in the context of direct impacts is also useful. So one could summarize these indicators as for more in terms of morbidity and mortality, but each of these numbers are very critical, especially if we are trying to create a report like post-disaster need assessment and further on. Can we go to the next slide, please? So what you see here is a dashboard that gives some one of the indicators, some of the indicators here related to nutrition related indirect indicator. So this is what you see here is using GeoNode, GeoServer, PyGeoAPI, and JavaScript. This is looking at anemia among pregnant women and in India, and these map visualization and graphics are specially made so that they can be imported directly into disaster management tools such as post-disaster need assessment, and we have many more indicators in this. So we are continuing to build our dashboard components with direct and indirect indicators, and as we see, these decision-ready information (DRIs) can be used by policymakers and decision makers alike. This is just the beginning, and we have lots of ground to cover. So, next slide, please. And thank you for your attention, and we are happy to interact with you during the webinar and also thereafter. Thank you. Contact address is available in the first slide of our presentation. Thank you.
Thank you very much for the presentation, Sumit. And next up, we have the energy impact, and this is also going to be a video with voiceover. So I will go ahead and play that now. And if any of the participants are having issues seeing the video, please post a question.
Hi, my name is Stefano Bagli. I'm the CEO and co-founder of Ecosistema, an environmental engineering company based in Italy. I will present the energy impact indicator developed under the umbrella of the OGC disaster pilot project. So climate change is significantly impacted the energy sector, affecting both the demand and the supply. So for example, during hot and dry summer conditions, we can have an increase of energy demand due to cooling of our rises and a decrease of hydropower production. This lead to potential energy shortage, resulting in blackout and economic losses. So in the framework of the OGC disaster pilot project, our aim is to develop a data-driven minimum viable climate service that is able to predict the energy demand and the hydropower production by accounting for future and current weather and climate conditions. The indicator can be used to assist the energy industry and the policy makers to support decisions for mitigation of energy shortage or for supporting energy trading, and also evaluate the impact of climate variability and change on the energy sector in general. The indicator will provide and deliver a time series forecast for electricity demand and hydropower supply, and can be used in a short-term or long-term forecast, including monthly, seasonal, or climate change projection. The climate-based indicator is generated and designed using a data-driven approach. In particular, we use advanced neural network model algorithms, such as the long short-term memory, LSTM, and the sashimi model. As an input, we need daily data on country energy consumption and hydro energy production. And as a covariate, we use the country's average mean temperature, precipitation, wind speed, and solar irradiance. The indicator has been developed and validated for Italy, but can be easily replicated to any country, region in the globe. The data for Manitoba were not available at daily time step. That's why we decided to develop and test the indicator where the data are available, for example, in Europe or in Italy. So the indicator as a target variable, so the target to be predicted are energy consumption and hydropower energy river generation. As a covariate, we use temperature, precipitation, wind speed, and solar irradiance. The historical data set has been collected from 1973 to August 2023, so we have more than 60,000 series of data. And the source of historical data concerning the climate data are the Copernicus Climate Data Store, in particular the ERA5 historical real-time data. And for the hydropower production and the electricity demand, we exploited the data available from the ENSO e-Power database. In order to acquire the historical data concerning the climate variable, we exploited the Copernicus Climate Data Store API, and here you can see an example of the code that you can use in order to download all the climate variables. The climate variables and the target variables collected can be analyzed and can be pre-processed. Here you can see the time series of the 16,000 daily time series data sets. And the next step is to pre-process the historical data in terms of cleaning data, so remove the outliers and filling the missing value. And then we have a feature engineering, means create new features, for example, calculate the moving average or the rolling standard deviation. And then finally, we normalize and standardize the data in order to be used by the artificial intelligence algorithm. Here you have some code example of the lagged feature that has been created for the different climate variable and also for the target variable, and the normalization techniques that has been implemented in the model. Once we have the data available, we can define the artificial intelligence model. Here, some details about the parameter that we use to train the model. So the target is the energy, the covariate are temperature, precipitation, wind, irradiance, and the month, the day of the week, and the day. And then you can see some technical parameter that has been used to train the models. So the model can be trained over a test and train data set. So we have splitted the entire data set in 80% of data as a training and 20% of data as a validation. In our validation data set, we can compute for the different models, the STM, the sashimi, the error metrics, and we got good results in terms of energy demand and both hydropower production. So after the model validation, the model is then prepared for the production. It's possible to save the trained model and then use and deploy the prediction through a Dockerized version of the model with a microservice. So these are the line of the code that we use to prepare and save the trained model. So once we have the model ready to be deployed, you can use the model in order to provide long-term forecast. So in this case, we provide a monthly forecast on daily basis, and both for hydro production and energy demand. And we are feeding the model with also the prediction of the climate variables that are available. And the results are pretty good in terms of performance. Or you can use the models in a short term using only this prediction is purely based on the recursive value of the target variable, and also in this case, in a short-term prediction forecasting, we have good results. So, as a conclusion, the energy indicator benefits can support proactive resource allocation. So, for example, you can utilize predictive energy production insight to foresee possible shortage and blackout, to pre-allocate generators and resources to essential services and the area at risk. So, for example, for the critical infrastructure, you can design and reinforce essential facilities for energy resilience. You can combine energy forecast with an emergency response system for unified situational view, and can be used also in a post-disaster restoration in order to guide the activities during post-disaster scenarios. And the data-driven decision-making can empower leaders with real-time projected energy data for strategic emergency management. So thanks a lot for your attention. If you have questions, I'm here to answer to your doubts or questions. Thanks a lot.
All right. So that concludes the presentation of the decision-ready indicators for the drought scenario. Looking at the time, we're at 11:30 here, so a little bit into the break period, but we do want to have some time for some questions and answers. I've pulled up the indicators that were presented here in this session, and if anybody has any questions for the presenters, now is a great time for that. So you can ask those questions in the Q&A panel in your GoToWebinar control panel, or you can also raise your hand as an attendee, and we're happy to unmute you to interact with the speakers. And Josh, also, if you have any kind of key takeaways or questions that you would like to ask, please feel free to do so.
Thanks, Trent. Yeah, one thing that I might note, hopefully you took away from this, is that it is quite complex to involve the various stakeholders in drought, because drought literally gets its fingers into so many different stakeholders, impacted populations, and impacted processes. And this was very much the goal of working closely with the Manitoba Emergency Management Organization and the many other organizations and the stakeholders in the province of Manitoba who cooperated and coordinated with this activity. There's a terrific realization on the part of those organizations that they're not all working from the same script and the same information, so that they can work towards achieving the sorts of coordination that they are able to do in, very acute circumstances, but not so much, day to day, week to week, that persistent shared awareness that is needed for these climate-related hazards and disasters such as drought. So that's why drought is special, and we very much appreciated working with the province of Manitoba on those special challenges that it provides. Yeah, so there is a question from Alan Leitner. One might assume that for a province, region, or state, you would want a capability to use all these models to address vulnerabilities and threats. How is this capability built? Well, there really are two approaches to answering that question. One is infrastructure, and that has to do with having the capabilities to gather the necessary information, do the necessary processing workflow, and then disseminate the results. And so there are many technical aspects to that, from data sharing standards to the availability of things like cloud-based infrastructure and mobile applications. Many of these aspects were examined. For example, containerized workflows, service interfaces, and we'll hear about some mobile applications later. The other part, though, is organizational behavior, as we noted. How do organizations take account of, invest in, engage with these workflows, particularly a framework of capability to do the workflows that are needed for the hazard that needs to be addressed and the time frame in which it's occurring. So, excellent question, and very much the gist of the work that we've tried to do here. Another question which has been raised: how can we engage more with stakeholders? Yeah, and I think it's a very good point that our ability to engage with a variety of stakeholders in Manitoba really was mediated by the emergency management organization, which set out to address specifically that challenge. And so having the right partner organizations to say, yes, every morning we have something different, but we do need to have a longer and more general perspective as well. And so kudos and thanks to our partners at the Manitoba EMO for their activities and for their vision. One other thing we can note, and then maybe we'll go to the break, is that among other things, the Manitoba EMO helped to organize and invite us to work with them on a workshop in Winnipeg, where we were able to sit down face to face, both share our capabilities and concerns with these organizations, but also they put together a terrific simulation, tabletop exercise of complicating and cascading hazards to really push on that. Are we sharing information that's needed when these circumstances, many of which seemed in the past quite far-fetched, and now they just do not seem like things we can ignore anymore. So we would love to take that as a template for other workshops that we can do to help the ensemble of organizations in a particular region addressing particular or general types of hazards and disasters, to work on that realization and responsibility as well. Right, that looks like it, Trent. Should we go to a break here?
Yes, that sounds great. So we'll take a 10-minute break so we can stay on schedule. So we'll start back at 11:50 Eastern time. And we've got an exciting lineup scheduled for the second half here. We'll start out with the wildland fire scenario with the decision-ready indicators and also the immersive visualization from Duality. So look forward to speaking to everybody in 10 minutes. Thank you. All right, welcome back. It's 11:50, so I propose we go ahead and dive back in and get started. Josh, I've made you presenter if you'd like to share your slides on the wildland fire scenario. You're still muted.
There we go. Everybody hear me, I hope. Welcome back.
Yes.
Hope you got a quick three course lunch here, and we're ready to roar away at wildland fires. So let me show this. Not the main screen, PowerPoint. There we go. All right. So our second scenario for the disaster pilot had to do with aspects of wildland fires. And this is, you've probably heard the term wildfires more often, but not all wildland fires, so fires at the boundary of or beyond the boundary of the developed built environment, but occurring in many cases and dangerously at the interface between the built-in excuse me, and wilder environment. But not all wildland fires are wild. Some of them are prescribed fires, and this speaks to the issue of what is going on with wildland fires, specifically wild but not limited to wilderness, or wilderness but not necessarily wild. So fires in the natural environment are natural. They are not only occur naturally, but they're really important. And we're realizing an increasingly important part of how a landscape stays resilient, stays sustainable, and stays resistant, in fact, to more catastrophic fires. And this is a hard lesson that we are learning as we speak. So it's a natural process, but in many cases, many ways, it's been hijacked by development and amplified by climate change. The need for resilience, the level of resilience that's required, has really been amplified by increased heat and drought, by invasive species, which are turning a lot of viable plants into viable fuel. And this was particularly the case in many northern parts of Canada, but are also cases where there are borer insects that are killing large amounts of trees and turning them into firewood. And it's increasingly complex, increasingly inevitable, but where exactly and when exactly and to what extent fires will occur is highly variable. It's some mixture of the availability of fuel, the risk of that fuel igniting, the weather conditions that either cause ignition through lightning or exacerbate ignitions through high winds and so on. Increasing effect of carelessness, but also of that intricate and extended interface between burnable material and where people live in the urban, suburban, exurban sprawl that increasingly contacts all the places that need that fire component of remaining sustainable, but don't get it because that places those developments at risk. So that contradiction, we need fire, but we don't want it here. And climate change is just making this much worse, is why this is a really important hazard to have the best information for, to have the best coordination for. So it's a volatile juxtaposition of long-term trends, drought, vegetation trends, invasive species, policies, forest management practices, residential developments, utilities hazards to feed those residential and business developments. Medium-term elements, seasonal air quality, accessibility, impacts, and extremely short-term burn episodes. So over decades, these situations develop, but the burns can be, as we very, very sadly discovered in Maui, can be very fast. And management practices, policies, information set up for slower events can be quickly overwhelmed by these very fast moving burns and evacuation challenges. So this fire, as we noted, plays a large role both in the ecosystems of the environment and in disaster ecosystems as it plays a role in these cycles of complicating and amplifying disasters, drought, fire, landslide, and other effects. So we have a number of exemplar indicators having to do with the proclivity for the risk of the threats of wildland fires and indicators of decisions that can be made both to be resilient in the face of it, to adapt to it, but also to look towards mitigation. Fire fuel work by Cherry, ignition risk work by CompuSalt, evacuation work by Skymantics Europe, health impacts from HSR, and a new element here, immersive visualization brought to us by Duality. And again, please work up your questions and concerns. Use the QA box to pose some questions that our participants have many, although not all, of the answers to provide you with. With that, let me turn it back to Trent and let's hear about the actual work. I think somebody needs to unmute here.
Yes, sorry, I was talking and also muted myself, but I have unmuted Jerome. I'm not sure if his audio is working. So Jerome, you should be unmuted. We see the green microphone next to your name. All right.
Should we swap?
And he is logging in again. I hope that'll work.
We'll give him just 1 minute, and then if that doesn't work, we will go to the ignition risk next with CompuSalt, and I will go ahead and get those slides ready.
Can you hear me now?
We can, yes. Thank you, Jerome.
Sorry for the trouble. Hi, Jérôme Serui from HRS. I'd like to present our work on the wildland fire fuel indicator workflow. Next slide, please. Right, so quick overview. I'll talk about the objective that we try to achieve, our approach and methodology, a quick demonstration, what we managed to achieve, what's next in terms of future improvements, and the business value of our work. Next slide, please. So our objective was to develop an indicator workflow for wildland fire fuel based on our Gnosis map server, which implements several OGC API standards. The one input for the workflow is the Copernicus Sentinel-2 managed by ESA, specifically the level 2A data that includes the atmospheric correction. We use a machine learning model for the classification, random forest, which we trained on known fuel vegetation types from continental US. So the different OGC API standards that to which this workflow is available includes OGC API processes, including the Part 3 extension for workflows, OGC API tiles, coverages, maps, DGGS. And the work that we did built on previous efforts from the OGC Climate Resilience Pilot, also previous OGC test beds. Specifically, we relied on several performance and capability improvements to our Sentinel-2 data cube, which is available from our Gnosis Map server demonstration endpoint. And we also shared several climate-related data sets from the Copernicus Climate Data Store, which we also worked on as part of the Climate Resilience Pilot. Next slide, please. So the approach is basically to classify Sentinel-2 level 2A imagery into 10 high-level vegetation fuel types, and then in additional steps maps each of these types to an approximate fuel density, but this is really a rough guess. We're using the random forest classifier from scikit-learn Python library, and we train on the US vegetation fuel types for 2022, available from landfire.gov. In that data set, there's very large number of vegetation types. So what we did is to map these to basically the two-letter codes, which gives these 10 different high-level vegetation types in order to have a better result from the random forest classification. The training area was the Fish Lake, Utah, and also a surrounding area to the northeast, as well as Mount Adams in Washington State. And for both the training and for the actual input to the workflow, we use our Sentinel-2 data cube, which is based on open data from AWS, which is managed by Element 84, which is shared in the form of Stack and Cogs, Cloud Optimized GeoTIFF. And so we use 3 different seasons, so the spring, summer, and fall, 10 days interval, both for the training and the classification. And we also do an extra pre-computation to compute an enhanced vegetation index. Also, we apply pre-filtering of the cloudy region based on the Sentinel-2 scene classification layer. And the indicator can actually generate data for any spatial region or time, currently between 2016 and 2022, but the quality of the results may vary due to the limited training of the data. Next slide, please. So this is the original the fuel vegetation types from the landfire.gov dataset that we use for training the data. It's also available from our map server. Next slide, please. And this shows how it was mapped to the 10 different vegetation types at a higher level. Next slide, please. This is the Sentinel-2 dataset, which is also available from our server. Again, it's a global land coverage. Yeah, next slide, please. This is the Fish Lake, Utah training area. So you can see on the left the original vegetation type, and on the right the high-level types that it was mapped to. Next slide, please. This is the additional area that we use from Mount Adams and Washington State, the high-level vegetation types. Next slide, please. And this show here at the top, you can see the larger area that we use. So you can actually see the Fish Lake in the bottom left corner, quite small. So we use a slightly lower spatial resolution, but a larger area. And we combine these different data sets. So we trained it in 3 separate steps and combine these random forest classification trees for the model. And at the bottom, you can see the lower level vegetation types that it was mapped to. Next slide, please. Here you can see the scene classification layer from the Sentinel-2, and on the right, the natural color, red, green, and blue band. So we actually use all of the bands, but here you can see some typical, the red, green, blue, and the scene classification layer specifically. Next slide, please. Here you can see the color mapped enhanced vegetation index and the EVI equation on the left, which also makes use of the near infrared band. Next slide, please. Here you can see for the 3 different intervals for May, July, and September 2022. At the top, the red, green, blue, and at the bottom, the enhanced vegetation index. Next slide, please. Here is the larger area with the EVI. Next slide, please. And here the scene classification layer at the top and the red, green, and blue bands at the bottom. Next slide, please. And so here is our executing our workflow in our Gnosis cartographer processing client. So you can see that we access our server, we select the random forest classification process for fuel vegetation types, and then we select an input collection, which is our Sentinel-2 data cube, also offered from our same API endpoint. Next slide, please. And here, this is the workflow that this generates, the execution request, making use of OGC API processes part 3 collection input, so that the collection basically is a first-class object that just points to the Sentinel-2 collection. And this is valid for any area or time of interest. Next slide, please. So once this is done, you can actually make OGC API maps requests from a virtual collection, and we deploy this as a virtual collection, the S2 vegetation fuel types, which is also available from our server, and you can make a request for a specific area and time of interest and a specific resolution of interest. So this is the actual result of the prediction for the Fish Lake area. Next slide, please. And this shows how this was mapped to 0 to 100% fuel density based on those fuel types. And you can see this is a map request, but you can also make coverages requests. You just replace the /map by /coverage. You can also make coverage styles or map tiles request as well. Also DGGS to explore the results. Next slide, please. And this is the result for the Mount Adams area. Next slide, please. And this is a region slightly northeast of the Fish Lake. Next slide, please. So what we managed to achieve is to deploy both the vegetation fuel types and the vegetation fuel density as a virtual collection from our OGC API service, and also available to execute through OGC API processes. At this point, this is purely for demonstration purposes, so we'll need to put in additional efforts and validation for this to have any actual practical value. Next slide, please. So this is the other data sets that we're sharing from the Copernicus Climate Data Store, the fire danger indices. So this is also a temporal data set, which is comes from climate data as well. Next slide, please. This is another climate data set from the Copernicus Data Store that we make available through the API coverages. So here you can see the precipitation at a single pressure level. Next slide, please. So the next steps, we were considering using neural networks instead of the random forest classification in order to achieve better prediction, especially for different areas and times of interest, and being able to better consider the full richness of the vegetation types. We want to improve the performance, for example, by keeping the machine learning model in memory. We still need to improve the performance of our data cube, maybe with additional caching, improving how we access the COGS through HTTP range requests. We want to update it with the newer scenes. Currently, it's limited to October 2022, and we'd like to make this an automated process to always bring in scenes as they're being added. Also, we want to consider additional inputs for the training and prediction. There's several other fuel-related data sets from landfire.gov, many examples listed here. And also those two data sets that I just showed on the previous slides could also be considered as inputs, but they're currently not. Most importantly, we'd like to assess the accuracy of all this and the value of the indicator for stakeholders, and with their feedback from domain expert, we could address some issues and implement improvements. Next slide, please. So the business value, so with changing climate, this exacerbates the risk of wildfire spreading. So by understanding the factors behind this, we can better manage it. So the availability of fuel vegetation is one of these factors, and the different vegetation types correlates to different density of fuels and the rates at which the fire may spread. So with imagery in the production model, classifying these vegetation types can help identify areas that are susceptible to high risk of wildfire spread. So by developing and making this available and further improving this indicator and demonstrating the interoperability with OGC API standards, so we hope that we can help stakeholders and responders plan and make better decisions to better prepare for wildfire disasters. Thank you very much.
Thank you, Jerome. And next up, we have CompuSalt with ignition risk with Colin. And Colin, I see you're on the web, so we're gonna unmute you, and I will present your slides. All right, we can hear you, and just pulling up your slides here.
Okay.
All right, floor is yours.
Perfect. Thank you. Hi, everyone. I'm Colin Withers, a senior software engineer here at CompuSalt. I've been working with them for almost 9 years. For those of you who may not know, CompuSalt's an international software company based out of Canada with subsidiaries in the US and Europe. All right, let's just go to the next slide. So our objective was using more modern OGC API to allow users to assess fire risk over like their defined areas. So we wanted to create an OGC API process accessing the data, which was stored in a data cube, and then have the result be outputted into an OGC API coverage. We wanted to make sure that the index we created used multiple fire factors, not just temperature and moisture. So we made sure to incorporate wind speed, precipitation, soil moisture, humidity, and normalized differential vegetation, among a couple others. Next slide, please. So the data we used was the ceasefire data cube. It's a global data set with quarter-degree resolution, and the data dates back to 2001. When we initially got the data cube, it had data up to 2021, and we've since been harvesting the data to keep it up to date, so it's recent to the latest week. The data cube contains multiple different fire indicators, such as like atmospheric, vegetation. It's not just over the sea, it's also over land, of course, despite its name. Next slide, please. So some problems we encountered was with the data cube. It was the first time we worked with data cubes. It's a very flexible storage data type. However, it requires more custom code in order to interact with it. They're also large in size, which makes performance a large consideration. And it seems like it's a bit more of an emerging technology where there's fewer libraries already written and open source in order to interact with it. So we chose to use Python because it had the best support, and using the Xarray library to work with it. But it isn't yet optimized for performance. So that's one problem we were having. Next slide, please. So the approach we took in order to create the fire risk indicator was to combine. So first off, we allowed users to view the ceasefire data as coverage APIs. So that's what you see in the four corners there. They're all different indicators as their own layer. And then we created a processing service to give the resulting index from all the individual factors. And then we updated that index to return a coverage service so that you could visualize the result of that coverage service on the map. And all of that is executable with a user's criteria. So next slide. I'm going to show a short demonstration from our video here.
Yep, let me hold that up. I think we have that locally, so just a second here. And as a heads up, the sound will not come through Play This Way, so you may need to talk through it, Colin. Yeah, when it's uploaded to the GoToWebinar ahead of time, we can play the sound, but
I don't have the script on hand for it.
all right, let me see if I can, well.
Incidents and events an organization is supporting. In this case, a portfolio was created based around Fish Lake National Forest wildfire that occurred in Utah in 2023. Our scenario will show the progression of a fire potential index, FPI, leading up to the fire that first started on August 4, 2023. This will be done by running the OGC API processing service to show the FPI at different intervals prior to the fire. We will begin by drawing an area of interest over Utah. This chosen area will serve as the focal point to run the processing service. Notably, the bounding box coordinates have been pre-populated for your convenience. Next, we will input a date that predates the occurrence of the fire. The Fire Potential Index, FPI, is then displayed on the map as an OGC API coverage. The risk levels are visually represented in a gradient from low to high, employing the color styles of blue, white, and red. Areas of no risk are omitted. We've repeated this process using multiple dates to illustrate the incremental escalation of risk leading up to the occurrence of the fire. More results were added for analysis. In addition to visualization of the FPI-related coverages and processes, the workflow will include data over the area showing things such as road networks, fire perimeters. The fire perimeters and containment zones were created using our Go Mobile product and OGC Geo packages. Within WES, various sources are harvested for analysis and predictive modeling, including OGC APIs, features, coverages, processes, and records. The data used in generating the processes was the Ceasefire Cube, a global dataset for seasonal fire modeling in the Earth system, containing 21 years of data from 2001 to 2021 in an 8 days time resolution and 0.25 degrees grid resolution. A diverse range of seasonal fire drivers, atmospheric and climatological variables, vegetation and socioeconomic variables and other target variables, such as burned areas, fire radiative power, and wildfire-related CO2 emissions. CompuSalt started with this and created harvesters to keep the data up to date. We then used OGC API coverages and processes to create a means of visualizing the data. OGC API coverages provide a global view of the data, with a temporal capability to allow users to see the changes over time for any particular variable involved in the fire potential index calculations. OGC API processes provided the framework to allow us to create a workflow where users can obtain the fire potential index over any area of the Earth at any past or present time. In conclusion, through this pilot initiative, we developed a fire potential index that transforms analysis-ready data, ADR, from a ceasefire data cube into decision-ready data. This data is then visualized using OGC API coverages, contributing to more effective disaster response and decision-making processes. Thank you for viewing this video showing the utilization of CompuSalt's Web Enterprise Suite in support of the OGC Disaster Pilot 2023, focusing on D107 Wildland Fire Ignition Risk Indicator workflow.
All right, thank you. Colin, did you have some more slides?
There's 2 or 3 more. So basically, we've like our accomplishments in this this project so far. We successfully made our processing services, allowing us to change ARD data into DRI data. And we updated our West catalog and publishing flows to correspond with that. Okay, next slide. And then improvements, largely based around performance. Dealing with data cubes, as I mentioned before, was had some issues, and there's multiple ways we can improve that, as well as performance related to OGC API coverages, and some suggestions we could do at downscaling the data or implementing tiled responses. And next slide. That's it. Thank you.
Right. Thank you, Colin. Appreciate that. So next up, we have the evacuation with Skymantics Europe.
Okay, yes, thank you, Trent. Can you hear me well?
Yes, we can.
Excellent, perfect. Okay, so thank you, Trent and Josh from OGC to organize the pilot and this event. And thank you also for the sponsors for making this possible. My name is Antonio Correas. I'm with Skymantics Europe. We are an innovation company providing technology consulting and research services to the government and the private sector. And here I will talk about the D109 component, which focus on developing indicators for wildland fire evacuations. Next slide, please. So when a fast-moving disaster happens, such a wildfire, the task of the protection and the evacuation of the population affected is a very complex problem, not only because it involves stakeholders beyond Earth, climate science, and first responders, but also because it's involving other stakeholders like law enforcement, municipal, county authorities, and EMTs, who have the responsibility to protect the population and to organize evacuations. And of course, we have the population itself as a stakeholder here. But also the process of the evacuation itself is very complex because it requires knowledge about these three aspects at the same time, which is first is the fire severity and the evolution. Then you need to know very well the capacity of the road network to sustain an organized evacuation. And then also very, very importantly, you need to know about the vulnerability of the population itself. This latter aspect is difficult to introduce in the decision process of evacuation, mainly because of lack of accurate data on demographics and socioeconomic data, and also the processes that are based on the population vulnerability. Those are mainly lacking. So the goal of D109 was to produce a number of decision-ready indicators that emergency organizations can use to prioritize population evacuations based on these three factors working together, and also help them strategize their evacuation plans and the resources by being able to run different scenarios and achieve predictability when a wildfire actually happens. Next slide, please. So this slide shows the decision workflow that leads to the production of the decision-ready indicators. The areas of interest that we implemented were Fish Lake, Utah, and Winnipeg, Manitoba. The source data was on one side was the fire ignition and the fire spread likelihood. Then we have the road network data. And then we have demographics for individuals and households in the affected neighborhoods. We enriched the demographics with health indicators provided by HSR Health that determine the health vulnerability risk of the population groups of the affected population areas, which are based on respiratory disease incidence and also chronic kidney disease incidence. Then what our evacuation engine did was first it determined the neighborhoods that were exposed to the wildfire based on the distance to fire and also to the vulnerability of the population. And then based on the mobility profile of the people living in those households in the neighborhoods affected, we use our routing engine to calculate the evacuation routes, considering constraints due to proximity to fire, which may make that some road segments would be blocked. Then we also incorporate the possibility to make updates to the roads, to the road network, emulating the actions of responders in the field who can update the status of the roads based on the observations in the field. So for instance, if there are fallen trees on a road or due to embers, they can observe that a road is not usable for evacuation. Or also there could be new roads that can be built by bulldozing an open area and make it fit for evacuation. Then the resulting DRIs that you see in the little blue box on the right, there would be on one side we have the geometric polygons of the neighborhoods that we defined at the level of census subdivisions, more specifically block groups. Then we have for each of them we have the evacuation level to be notified to the population. Then the evacuation route preferable for the population living there, and then also together with special needs or instructions that that population may need. And then these indicators, they were exposed via OGC API, which in this pilot were used by Duality for the visualization in their immersive visualization component. Next slide, please. So So a big innovation in this component was to figure out how to recreate a population of the demographics accuracy and the scale that is needed for an evacuation scenario. Not only using statistics, but creating an actual digital twin of the population, considering that census and health data, they are incomplete because they're based on public service of the population samples. So we used our tool, which is called Data Genesis, which is our new synthetic population generation engine. And that's a tool that uses artificial intelligence to transform samples of population, for instance, from a census, to an actual population dataset that can be created at the required size, and that can also be tweaked and aged, and maintains the reality of the relationships between the variable, and also allows aging into the future for alternative scenarios. So the advantage of the approach of using synthetic data is that if emergency organizations have accurate local data on the populations, they can use it to generate a synthetic twin, which removes the personal identifiable information, thus mitigating the privacy issues that they may have due to being real data, and allowing for safe collaboration and sharing. Next slide, please. So this slide shows a sample of what synthetic individuals and households look like. As you see, it's just a bunch of tabular attributes that can then be used for visualization and analysis. You can see here, I think this shows that the population is not just a combination of statistical functions, but it is actual discrete data, also called microdata. And in the evacuation component here, this was very useful because we needed to create discrete simulations of population movements to determine the route capacity and time to safety, and also the vulnerability levels. which with only using aggregate statistics from census or from CDC, they would not have been possible. Next slide, please. Thank you. So this slide shows the architecture point of view of the workflow. You can see that the data sources that we use for synthetic population generation were the census and CDC. Then the synthetic data was enriched by HSR health attributes. Copernicus satellite data was used to create a fire risk index visualization layer that I will show now in a moment. And then OpenStreetMaps was used for the road network. This was input, so both the OpenStreetMaps and the fire risk index data, they were inputs into the routing engine to calculate the evacuation routes and the time to safety, considering road constraints due to proximity to the fire. And all this, it was all published via OGC APIs used by other components such as duality component. And also we developed an in-house demo client that I will show next to show you how the workflow works. So if you can go to the next slide and with the video, I can talk over it.
Okay, you should be seeing the video now. Oh, we may have to unmute you.
Oh, sorry, I was talking, but I was on mute for some reason. Do you mind replaying the video again, beginning?
Sure.
Thank you. Yeah, I don't know why I was on mute. Okay, now I can. Okay, yep. So there are several steps here. So first, you can declare the fire, and what we are showing here is the grid of the fire danger index from Copernicus. So the user can select where the fire has been declared. So we assume that the fire is happening there, and then next, the user can set the evacuation destinations. This is an optional thing to adhere. If not added, then the engine will just select the safest municipalities to be evacuated to. And then it will calculate the vulnerabilities. You can see there the different block groups. If you select one, so there are some that are more rural, more urban. So if you select one of them, it will give you the data on the block group, the type of the population, how many do you have with respiratory diseases, and you have the priority of the evacuation there. You see, it's different here because it has a higher elderly population and sick population. And then the evacuation routes, which are shown there, and can be also downloaded in GeoJSON. So now I'm showing here the same scenario, but I'm going to play with the block and creating new routes there. So the fire is declared in the same place, and the evacuation destination is also in the same place as before. But what I'm going to do now is I'm going to assume that an agent in the field observed that the smoke plume to this fire went to southeast and made all the roads there unusable. You see all the roads that are north of Mount Dutton are unusable. So I'm going to block all those roads. But then the first responders are also able to draw a new road that will make the evacuation more expedite for the junction municipality. So we are assuming that they are able to bulldoze an open area there and create a road there. So I drew the new road, and I will recalculate what the evacuation routes will look like here. And just a reminder that these functions of blocking and creating new roads, this would be something that could also be input in a mobile app. by agents in the field, and it's something that could be developed in the future. So here you see that as a result, the population from the municipality here, Junction, they cannot use the block groups, the block roads anymore, but they can use part of the new road that was built there. So that first segment of the new road was useful and made the evacuation more expedite to the evacuation point. So that was for the demo. Thank you. So you can go back to the slide, please. Perfect. Thank you. So we achieved the objectives of the pilot. The most important was to shift the decision basis for evacuation priority calculation into being population-centric based on the vulnerability of the affected population. This vulnerability can be the demographic. For instance, if there is a high proportion of elderly people in the neighborhood, it can be health-based. For instance, if there are many people with respiratory conditions, or mobility-based, for instance, families without cars. Of course, we developed also a component that is fully interoperable via OGC API standards. And we also created a what-if scenario analysis baseline that allows emergency responders to play around with foreseeable scenarios and detect vulnerable areas in their jurisdiction or gaps in the road network and resources, so that they are able to improve or to assign extra resources or disaster mitigation techniques where it is needed. Some limitations that we found when working on this were, first, there was some lack of population data at the local level. Thanks to using the data genesis, we scaled down census and CDC data into synthetic population datasets that proved accurate. However, local authorities may have more granular data, so this is something that can be worked in the future. Also, OpenStreetMap has inaccuracies in the possible road speed that can be achieved in the road segments, but this was mitigated also with our AI algorithms that are able to calculate vehicle speed per road hierarchy based on some terrain elements and features. And finally, we also missed an integration with models that would explain the behavior of the fire spread and the smoke plume. So our prediction of the fire status that led to how long it would take to make a population affected, it was basically on overall values. So on next slide, I will just talk about some next steps for future work. So we would like to first to support multiple fire sources in the same scenario to account for more realistic situations. Then, as I mentioned before, work with local and regional authorities to incorporate local data on population demographics and health conditions. That would be very, very useful to have data that is more complete and accurate at the local level. And thanks to our synthetic population engine, we can remove the privacy concerns that the authorities with this data may have by still maintaining it accurate and useful, but safe to share. Then we'd like to integrate real-time fire spread and smoke plume models to account for real fire behavior. And then finally, a high-value application would be to integrate this with an actual mobile app for agents in the field that allows them to update the road network according to observations. So thank you very much. That's it for my presentation, and I will be ready to take questions if thank you.
Thank you, Antonio. We did receive a couple of questions during your presentation. I tried to assign those to you in the Q&A panel, so you should be able to respond if you'd like, and we can also address those in the Q&A session. Up next, we have HSR Health with Paul, and I think we're going to start off with the video. Is that right, Paul?
That is correct. Then we'll go into the couple of slides that I got.
Okay.
Wildland fire frequency, severity, and duration are increasing throughout the western United States and around the world. While 80% of wildland fires are accidental, They are exacerbated by climate change, and their effects on community health, the environment, and wildlife is substantial. Identifying where resources and personnel need to be sent within the affected areas to help the local population is a core part of the disaster response and relief effort. To address this need, HSR.Health has developed, through the support of the Open Geospatial Consortium's 2023 Disasters Pilot and pilot sponsors NASA and USGS, our Wildland Fire Health Risk Index, which has been tailored for the western United States. Wildland fires affect vulnerable populations and contribute to negative health impacts through the flames, smoke, and damage to infrastructure. The primary health effects include impacts to cardiovascular health, respiratory health, mental health, direct fire-related injury, including burns and heat stroke, and increased susceptibility to respiratory diseases, including COVID-19. The Wildland Fire Health Risk Index identifies a priori the health and medical needs of the impacted population and informs emergency response personnel, public health officials, governments, economic development, city and civic planners, and global public health organizations the information that they need to take preventative measures before a wildland fire occurs to limit its impact, speed response efforts during a disaster scenario, and guide recovery efforts in the aftermath of a fire. Shown here is a dashboard built in the ArcGIS Online environment of the Wildland Fire Health Risk Index for the western United States, overlaid with historic and current wildland fire extents that indicates the regions of relatively higher health impacts from wildland fires and where resources may be more at need. The underlying health and social data of the population is included in the dashboard and associated layer, a subset of which is shown in the highlighted table. We utilized the NAPSIG symbology for the risk index, which was recommended for layers pertaining to disaster response based off of input from FEMA. The Wildland Fire Health Risk Index was utilized by Skymantics as an input into their wildland fire evacuation workflow. Additionally, we worked with Skymantics to utilize synthetic population modeling to predict the prevalence of chronic health conditions to the census tract administrative level. The Wildland Fire Health Risk Index is calculated through a weighted combination of the health and social characteristics of the impacted population. The risk index identifies populations at higher risk of adverse health outcomes in, or those with chronic conditions that are exacerbated by, a wildland fire scenario. The data for these factors was sourced from the U.S. Census Bureau, the U.S. Centers for Disease Control and Prevention, USGS, CompuSol, and Skymantics. The primary standards utilized for the Wildland Fire Health Risk Index include WMS, WFS, OGC Features API, ISO 3116-2, GeoJSON, GeoParquet, and Cloud Optimized GeoTIFF. During this pilot, we began researching standards relevant to the data utilized, including ISO 3116-2, ISO TC 215 Health Informatics, and HL7. Future pilot efforts should continue to explore standards related to health and demographic data and data exchange. The Wildland Fire Health Risk Index is published on HSR.Health's OpenGeoMD platform, which is deployed in the AWS cloud through both an Esri ArcGIS Enterprise stack and GeoNode and GeoServer open source stack, as well as through other catalogs made available through the pilot. Each of the layers for the Wildland Fire Health Risk Index that are available in the OpenGeoMD platform can be imported into a user's own system through a WMS GET request via a link in the top right. Additionally, the data is made available through an OGC API instance as shown here. The Wildland Fire Health Risk Index will remain available on the OpenGeoMD platform as a persistent demonstrator. To expand upon the capabilities of the Health Risk Index, it will be incorporated into our generative AI-based GeoAI for Health platform that also incorporates a decision support AI based on a large language model to provide real-time guidance and supplementary information to emergency response personnel to aid in responding to the impacted populations in such a dynamic scenario. In future climate and disaster-related OGC pilots, the capabilities of the indicator can be expanded through incorporating climate models and additional synthetic population modeling to predict the health impacts and severity for future wildland fires in the western U.S. Additionally, we can demonstrate interoperability through ingesting the outputs from fellow participants in this disasters pilot to enhance the capabilities of the Wildland Fire Health Risk Index. Thank you very much for watching this demo. For additional information, please visit our website or contact us at impact@hsr.health.
All right, thank you, Paul, and I'll transition to the slides.
Sounds good. You can start at slide 3. Awesome. Let me throw this over here. Awesome, thank you. So thank you everyone for the opportunity to present our Wildland Fire Health Risk Index, developed and modeled for the Western United States as a part of this 2023 disasters pilot. I hope you all enjoyed our demonstration video for our Wildland Fire Health Risk Index that was developed and modeled for the Western United States. I'll now talk a bit more about the exciting inclusion of generative AI into our disaster response indicators. Next slide, please. So generative AI, geospatial analysis, AI and ML data science, health analysis, and purpose-built LLMs to augment data curation are all powerful tools for analysis of disaster and global health issues. Our generative GeoAI for Health platform combines all of these analytical techniques into a novel and powerful platform for health-focused insights. When responding to disaster scenarios, it is important to have the right information available to aid in the response effort. However, feedback that we have gotten from FEMA has told us that emergency response managers are often inundated with excessive data. They need a solution that synthesizes and categorizes the data in a way that allows them to understand it and incorporate it by providing guidance on the most time-sensitive decisions that can be incorporated into their decision process. The generative GeoAI for Health platform speeds decision-making through enabling the synthesis of large quantities of data and indicators into concise guidance that can be readily acted upon. This improves emergency response efficiency through identifying the most immediate concerns, along with recommendations on resource allocation, and ensures equity in the response process by identifying the response best suited to address the needs of each vulnerable population. Next slide, please. The generative GeoAI for Health platform allows end users to ask health and disaster-related queries for wildland fires, such as what are the long-term implications of regional wildland fires on health outcomes, what are the areas that should have prescribed burns based on fire risk and populations at heightened risk of severe health outcomes from wildland fire, and what are the long-term implications of smoke plumes on health outcomes. Next slide, please. Thanks, probably delayed. So far, I've talked about some example queries and indicators that the platform can provide for wildland fire, and this is also applicable to drought as well. The generative GeoAI for Health platform provides insights into broad global health topics, incorporating our existing analytics of the Hurricane Health Risk Index, the Medical Supply Needs Index, the Bioaccumulation Health Risk Index, and indicators on consumer behavior into the platform. As we look towards the future, we have a roadmap to expand the capabilities of the platform to incorporate maternal and child care, care deserts, opioid abuse-related mortality, hospital readmissions, zoonotic disease spillover, and heat health risk, among others. Next slide, please. And I'll just talk through it. So the Wildland Fire Health Risk Index, as shown in the video, is published to our OpenGeoMD platform as a persistent demonstrator. The maps and layers are all available through various OGC open standards, and the demonstration videos that I showed today for both the drought and wildland fire scenario will be available on our YouTube page, as well as potentially the OGC's YouTube page as well. Next slide, please. Awesome. Thank you very much, everyone, for your time, and a special thanks to the sponsors and the OGC as you all make this pilot effort possible. Thank you very much for your time.
Thank you, Paul. All right. And next up on the wildland fire scenario, we're bringing it all together with immersive visualization from Duality. And I believe we're going to start with the slide deck there. Is that correct?
Yes. If you can start the slides.
Okay, the floor is yours.
Thanks. So I'm Sunil from Duality, and we'll be talking about and mostly we'll be presenting a video about the 3D immersive visualization of all the various decision-ready indicators you have been hearing about. Next slide, please. So a very brief introduction to Duality. You can visit duality.ai for more information. We have a lot of products and solutions for various verticals. But we create mainly virtual worlds for solving real problems. We have our digital twin simulation platform for safe, predictable, and resilient smart systems. On this project, a bunch of us got involved to right from art director to engineers to artists to our cloud infrastructure engineers to make this happen. Next slide, please. If you can play the video.
Hi there, and welcome to Duality's latest simulation demo, the OGC DP23 Wildland Fire Indicator Immersive Visualization. Many federal and state agencies, tribes, local land managers, and other stakeholders work together to manage wildland fires. Training, planning, and managing resources before, during, and after events are critical aspects of the strategies to combat them. The availability of past, real-time, and near-time data, together with their immersive visualization and the simulation of various possible scenarios, can immensely help stakeholders and decision makers. At Duality, we've developed a demo to show off a scenario that combines our digital site twin technology and our interactive visualization of data that would be important to combat these wildfires. The data, which are decision-ready indicators, also known as DRIs, are generated by our fellow DP23 participants from Skymantics, HSR Health, and CompuSalt. First, we created a digital site twin of the area of interest. Then we proceeded to overlay the DRIs over top. The goal is to provide extra context to people who are making the important decisions pre, post, and during a fire. This chart shows a quick overview of the system. On the left is the creation of the site twin, and the right the import of the DRIs. Both are converted into digital twins in our catalog and then added to a scenario that is run by our Falcon simulation engine. First, we start with creating the digital twin of the site. We selected an 84,000 square kilometer area around Fish Lake, Utah. This is our first time creating a digital site twin on such a large scale. Our previous largest example was a 200 square kilometer city. Creation, visualization, and simulation of such a large area presented many challenges, particularly on the compute resource front. We had to devise many innovative solutions to resolve them. To make this twin, we acquired 189 1-meter resolution DEM tiles from the USGS. After merging the tiles, the DEM was processed to generate imagery with the required resolution. Then for the texturing, we started with cloud and shadow-free Sentinel-2 10-meter resolution tiles. Through our GIS AI pipeline, we analyzed and classified the satellite imagery into 5 soil classes: whitish, light brown, medium brown, dark brown, and golden brown. Then we analyzed vegetation types, and then we created road and street network geometry using data from the US Census Bureau. We then worked with the OGC DP23 DRI participants to extract datasets from their respective APIs. Each of these datasets were further analyzed and processed to be ready to be consumed by our 3D digital twin pipeline. Through Skymantics APIs, we collected coordinates of the evacuation route's waypoints. Through HSR Health's APIs, we collected health risk and population health data for all of the census tracts in our area of interest. The right-hand side of this image represents example data from one of those tracts. Through CompuSalt's APIs, we collected a fire potential dataset and converted it into geometry. The right-hand side of this image represents an example fire potential dataset for 2 different dates. Fire potential values range from 1 to 100, where 1 represents the lowest fire potential and 100 represents the highest. Next, these 3 sets of data were converted into 3D geometry to be placed on our digital site twin. This image shows the evacuation route geometry. This image shows fire potential for grid squares ranging from 1 to 100. 1 represents the lowest fire potential and 100 represents the highest. The grid squares are 27.75 kilometers square. This image shows the risk indicator census tract boundaries. The geometry was built from these with the height based on data from ranges 1 to 7. In this range, 1 represents low risk and 7 represents extreme risk. This image shows the road network from the US Census Bureau data. And finally, this image shows the terrain surface derived from a height map supplied from a 7,000 by 12,000 pixel GeoTIFF image of Fish Lake, Utah. Now it's time to see the demo of the actual scenario. First, you see our site twin, which can be viewed from any angle, but we've provided 3 preset cameras on the right to choose from. We've marked the 3 angles in these images with a north direction. First, we turn on the evacuation route, which also includes arrows to specify the correct direction to travel. Next, we turn on the health risk, which breaks up the landscape into specific zones and then provides data for each. So for example, let's zoom into Zone 2, and then it reveals the data associated with that area. Or here's the data associated with Zone 8. Now let's turn on fire potential. The brighter yellow colors are an area of higher potential, and the more transparent yellow are areas of lower potential. Then we turn on fire spread. The day slider lets us scrub or play through the data as it relates to a 30-day period. So you see when we move through time, the fire spread data changes. The spread shown here is based on a simulation, and one of the advantages of our approach is the ability to view DRIs in spatial alignment with simulated or real fire scenarios. Now let's turn on several of our DRIs at the same time, and hit the play box to play through our 30-day period and see how the data changes. Some data changes daily, or as is the case with our fire potential data, we get a change in data every 8 days. A digital site twin of an existing location with immersive visualization, navigation, and ability to simulate various scenarios opens many opportunities for federal, state, and local government organizations, disaster response personnel, decision makers, aid organizations, and citizens to improve their fire response in the case of an emergency. Thank you for watching, and feel free to contact Duality for more information about our software or this project.
If you can bring back the slides.
Yes.
Some of the achievements, as mentioned in the video, this was the first time we created a digital site twin on such a large scale. We faced many challenges. Fortunately, we could resolve most of them, but it has been a great learning curve, both participating. This is our first time participating in OGC disaster pilot. It has been a great experience. And the second part is, again, this is probably for the first time we converted data sets into digital twins on such a large scale. 3 DRIs, different set of APIs, and bringing the data, creating digital twins, creating mesh for them, deciding what is the best way to overlay a given DRI, as well as when all the DRIs are together. So we feel very good about what we have done. It's a work in progress, but it has been a great achievement for us. That's what we think. And as part of this, we developed building blocks. We have all the building blocks for simultaneous and interactive 3D visualization of various scientific and research data sets. Next slide, please. We would like to, as part of other pilot programs, we would like to extend our pipeline to incorporate more data sets. And eventual goal is to help decision makers derive timely and meaningful insights. Next slide, please. Now, the demo you so in the video, you can actually go and play without installing any software. You can try for free Falcon Cloud. The link is here, or just go to duality.ai and you'll find a button to try this. So sign up, I would suggest, try the demo. We have other demos also of all our other scenarios we have been building. I highly encourage to play and send us feedback for this OGC pilot demo. Thanks for this opportunity. Thanks to OGC, thanks to all the participants, thanks to everyone, all the sponsors. Let us know if you have any questions. You can reach out to us at info@duality.ai, or you can ask questions right now or as part of this webinar. Thanks.
Thank you for the presentation and excellent video. So I think that wraps up the DRIs and the immersive visualization. So Josh, I'll hand it over to you for key takeaways from the wildland fire scenario, and also any questions that we want to address now. We are a little bit over on time, but maybe we can get to a couple of questions.
Well, I certainly encourage people to ask questions about this, because I think the key takeaway is that it is complex to provide support for decisions in the face of situations that can change quite rapidly and have different implications for different communities and different people because of the way that geography and weather and things like transportation work. So I think the key takeaway for me has been the importance of knowing about the people who are affected by this, could be affected, and the people that need to do something. There are many examples of the need to get the right information to the right person at the right time, but in the case of the fire occurrences and fire risk and resilience, it's never more obvious than in these cases. And of course, one of the main questions that all of these indicators raise is, how do you find them in order to make use of them? How do you find the data sources for a particular location and time and need for awareness? And I think that leads us, Trent, to the next section of our webinar here, the discovery and access of useful information.
Yes, that sounds great. Do you have any overview slides for this section, or would you like to just dive into the presentation from CompuSalt?
I think it's time for a dive.
All right. All right, so we're going to jump into the discovery and access section of the presentation here, and then we can circle back on some wildland fire scenario questions at the end. So switch over and present for Colin again here. Colin, are you able to unmute?
Yep, can you hear me?
Yes, we can.
So, similar to last time, we'll have a video halfway.
Okay.
Okay, so yep, Colin Withers from CompuSalt. Introduced last time, so let's just move on to the next slide. So we wanted to utilize our flagship software WES along with new OGC API standards to improve discoverability and interoperability of data access for the pilot. So to do that, we actually, that's probably on the next slide. So yeah, that was our objective. So let's just move on to the next one, please. So our approach in order to improve data interoperability is to register OGC APIs with our CSW catalog, primarily EDR, processes, features, and one major one that we didn't have, which would aid in this venture, was API records. So we updated, or we wanted to update our catalog in order to support OGC API records, and we also wanted to update our catalog to allow participants to publish and register services into our catalog. So we did that by creating a OGC API process service, which would allow anyone with access to publish their own services. And we also created a OGC records service using CCAN data as demonstration of functionality, as well as to help centralize some of those services if they were useful. So with that, we'll jump right into the demonstration.
This video shows the utilization of CompuSalt's Web Enterprise Suite in support of the OGC Disaster Pilot 2023. Focusing on the D100 Data Service Workflow Application Catalog and Registry. To aid in data discovery, we added support for OGC API record services in our CSW catalog. There is currently only one OGC API record service in our catalog. Let's publish another service. We created an OGC API process service to allow users to easily publish into our CSW catalog, portfolios, and Meta Manager. To add a service, simply open the West Catalog process by selecting the gear icon. Select the Publish Process option and select Next. We made a new OGC API record service for CCAN records, so let's publish that. Enter in the service URL for CCAN and select the service type, in this case OGC API, and select Next and Finish. Let's now look under the OGC API records category for our newly published service. Let's view the metadata about this service by selecting the Open Full Metadata icon. Select the Capabilities URL link to open the service in a browser. Select the HTML option. This is an OGC API record service that we made to improve discoverability of CCAN services around the globe. Here you can view multiple collections. Let's preview some WMS layers. The combination of our West catalog for publishing and discovery of services, paired with our new OGC API record service, improved data discovery and interoperability as part of the Disaster Pilot 2023 initiative. Thank you for viewing this video, showing the utilization of CompuSalt's Web Enterprise Suite in support of the OGC Disaster Pilot, focusing on the D100 Data Service Workflow Application Catalog and Registry.
So some of our major takeaways from what we've done here is now we're able to add record services, API record services to our catalog. We're able to add services and publish things through a process. And we created our own OGC API record service for CCAN services, which we think has the ability to aid in this disaster venture. Next slide. And so what we see next from these tasks is to allow those the records API services to be added directly to our map from within WES. So currently you have to, you can browse the catalog to help discover them, and you can open them in their own browser, but you can't add them directly to our map. So we demonstrated opening them in the browser and exploring them there, but we'd like to improve our software to give you more options. And yeah, that's it for our contributions to D100 catalog and discoverability. Thank you.
Thank you, Colin. All right, up next we have Dean from Safe Software. Dean, would you like me to run the slides or make you presenter?
I think I'll go ahead and be presenter, if that's okay.
Absolutely. You should have control now.
Okay, just waiting for my screen to come up. All right. And I'll just turn on my camera briefly. Okay, so yeah, we're just, I do appreciate everybody sticking around near the end here. I know it's been a long session. So we're just gonna dive into a bit of the work that we did around data cataloging, as well as developing some ARD climate data services. So there's really two objectives here. Some of the data cataloging stuff is, we're a bit new to that, so we're sort of doing some experiments on how to interact with and support different OGC standards around metadata and cataloging. And then there's a bit of an add-on here where we saw a need for analysis-ready data services. And so that development sort of bridges between D100 and D101, the work that we talked about earlier in conjunction with the drought scenario. So I'll hand it over to Kaylin, who's going to walk us through some of the metadata and data catalog stuff that we worked on.
Thanks, Dean. Okay, so if you want to just load the content. So the main objective for the catalog metadata service was discovery, indexing, and optimization of geospatial data from various open source data providers. This would ultimately allow users to provide data to the service automatically by extracting metadata properties in order to create a metadata catalog. Next. So this is the automated metadata harvester workspace. The idea behind this workflow is that a source file can be uploaded and an ISO 19115 XML document is generated on output. So here we're reading multiple feature classes from a file geodatabase as our source data set. We're using transformers, those blue objects, to extract key pieces of information. So assigning unique IDs, generating bounding boxes, creating timestamps before templating an XML and writing to text. Next. So we really see this workspace brought to life when it's published to FME Flow Hosted, one of SAFE's hosting applications. And here we can see the workspace configured as a self-serve app that allows users to automate the generation of their own metadata catalogs. So here the user's prompted for a source format and then is able to upload a data set. If your data is sitting in an S3 bucket, you also have the option to upload a source URL. And then the data is streamed back to you in browser with the option to download. Thank you. So this is the OGC API workspace. So one hosted on FME Flow. This allows people to query for metadata using the OGC API records protocol. Right now, this is only serving data sets used by SAFE in the pilot, but we could expand this to include other data sets as well. The main difference between these two workflows is that the OGC API records workflow has the ability to parse different query URLs and produce different outputs accordingly. So if we go to the next slide, there's a sample output from the OGC records API harvester. And next, thank you. So the key takeaway we learned is that the FME platform has the ability to improve the generation and exchange of other service and pilot catalogs. Next. So some of the some improvements or functionality we would like to kind of add to the self-serve app in the future is to improve spatial and temporal range detections, maybe optimize usage by allowing users to upload a route template, and be a little bit more dynamic regarding outputs. Another idea alternatively would be to extend the cataloging service to other participants for more robust feedback. Thank you.
All right, thanks, Kaylin. Yeah, so that's basically just a range of experiments that we did, and ultimately, our goal wasn't to build a comprehensive catalog like some of the ones we've seen, but basically feed catalog data to those. And so we'll have some automated approaches there to make sure that the metadata is up to date and more dynamic. So I'm just going to quickly go through in the remaining time a little bit under the hood of what we did for our climate ARD service. And the backstory to this is really that, again, we worked on an ARD component for both the disaster pilot 2021 and the climate resilience pilot. And so we kind of felt a need for it here. And so that's why we sort of wedged that into the D100. And the underlying assumption going forward is that I do believe that we need sort of ARD focused components to bridge the gap between searching for data, the data providers, and the actual application of that data to building DRIs, sort of like Josh's data flow diagram. So our objectives were to make ARD easier to consume for GIS applications and ultimately to support stakeholders. And the particular thing we're focusing on is climate data. So just get under the hood a little bit as to how we built an OGC API feature service, which would allow us to consume things like data cubes and NetCDF, and then ultimately produce those as GeoJSON features. And so there's the climate scenario, and this is downscaled regional climate model. And so you've got basically monthly time steps. And so the XY is really your spatial location, and the Z or is T, not elevation. And we have temperature and precipitation there, but we could just as easily add other environmental variables. So this is similar to what I showed very quickly earlier in the session. And just to walk through this a little bit more, we're splitting up the data cube into the 1,000 different layers, and then each of those raster grids, we're converting that to vector points. And the reason why we do that is it makes it a lot easier to take an OGC API features request and do a spatial temporal query across that data range. And so, yeah, that's what the geo package looks like. So that's the spatial database. And then this is what the OGC API features extraction workflow looks like. I'm not expecting to walk through this all, but we're going to freely share this on our knowledge base. You can have a look at it and play with it. And so you can see all of the OGC API parameters get applied to this extraction workflow, and that kind of supports the performance of it. And this is just the messaging service which handles the OGC API requests and hands that off to the previous workflow. This is all published on FME Flow hosted, or FME server in the cloud, hosted on AWS. That's the URL to access it. And again, just to kind of walk through a little bit about this query. So we've got, several million points. How can we filter that for the kind of the driest and the hottest over the next 40 years? And again, the historical mean we did was we looked at 1950 to 1980, and we averaged the precipitation by month for every location across southern Manitoba on about a 10-kilometer grid. And then we look at the future precipitation divided by that to get a normalized value of what the delta is. Is it getting wetter or drier? And so I was quite interested to see that yielded only about 50 or 60 points. We have a quick demo to run, and then we'll wrap it up. So this just shows our data inspector client interacting with the OGC API features service and setting the temperature and precipitation ranges that we're interested in, as well as these spatial temporal bounds. And then because it's hitting a spatial database, it doesn't have to interact with the whole data cube. It's just looking at those index values. And so out of a few million points, we just get about, in this case, 50 points. And we notice that south of Winnipeg, there's two sets of points, one from 2048, one from 2058, that actually satisfy those conditions. And there's also some record level metadata, which was important to provide some context as to where this data came from. And you can see what the actual precipitation and temperature values are for those points in July and August of those years. So that's pretty much it. Obviously, in terms of lessons learned, I think the bottom point, we found that climate services ARD is really useful to serve a pipeline, and then there's multiple indicators that could be based off the result of that. So there's this whole idea of indicator chains, because there's no one indicator that's going to tell you everything. And so I think rather than each of us working on our own indicators, I think there's some high value primary indicators that can feed secondary ones. And then there's this whole Goldilocks principle. What I mean by that is that it's always a trade-off, and you need a lot of stakeholder support to figure out what's the level of information that's useful to support decision making without overwhelming the user or the planner. And so early on, we did too much simplification, or it's too generalized, and it didn't give us high enough resolution outputs. So it's a bit of a balancing act, and it takes a lot of iteration. Yeah, automated metadata generation is important to support data catalogs and automation itself. And I think that ultimately improving access to data model results, as I said earlier, allowing the end users to actually interact with the data, see it in the local context, and play around with different business rules. I think that interaction with the data is really going to be key to improve stakeholder understanding of what's going on with the data trends, but also to improve the data, what we as data providers are giving to stakeholders, because they can give us feedback about what works and what's meaningful and what's not. So that's pretty much it. I think there's more work to be done. We're looking at providing more cloud native outputs, so that better support for downstream analysis. We're going to be publishing persistent demos and more information to our knowledge base. And I think the whole area of pan sharpening techniques, where you have coarse climate data from climate models that are sharpened by things like higher resolution local data, DEMs, and of course adding other business rules based on things like vulnerability, like Sarah talked about, and other climate variables. So just to wrap it up, open standards really opens the door to interacting and building things like indicator chains, and integrating the models together. And really, it's about being able to evaluate a range of climate impact scenarios, because we're not going to be able to predict a specific outcome, but if a system can handle a range of climate scenarios, it's going to be more resilient. And just going back to this whole idea, the past is no longer a useful predictor for the future. And yeah, different ways of interacting with stakeholders by giving them data to play with, I think is important too. Thanks. There's just a few links there from which you can follow up on and play around with some of the data services. Hand it back to you, Trent.
All right, thank you, Dean. Appreciate it. And then up next, we have Voyager Search and USGS GeoPathways. I'll make myself presenter here. Who will be presenting on this end?
Trent, this is Brian Golden. The presenters are actually John, but I'm not sure if he might be having some technical problems. Is he?
I don't see John on the attendee or the staff list.
Okay, then I'll be his backup. So can I have the presentation controls, presenter controls?
Yes. All right. You should have received a notification.
It's spinning, so I think it's coming through.
Okay.
Okay, there you go.
And,
all right.
Yes, we can see your slides.
Okay. So, well, first, if John can hear me and if he wants to jump in, he's welcome to do so. If not, I will take over. So let me open the slideshow. So this section of the D100 registration, search and discovery of data is really focused on the FGDC GeoPathways program. So we worked in conjunction with the GeoPathways program as one of 3 parts of this presentation. So the first thing I want to do is thank the almost 30 interns that really led the way for this work. So I'm happy to present that for them. Here, let me just get this. Okay.
Our world is increasing.
I'm actually gonna just go through the slides here, but we'll share some videos later. So this as an introduction to this section of the pilot, we've already talked about this some, so I'm going to go through a couple of these slides quickly. It's really to focus on best ways possible to make available this wealth of data that's coming in through sensors and also indicators or other types of services, as Josh mentioned earlier. It's just a plethora of data. To make that content available to people is actually quite hard. So the approach that was used in this section was to research several different open source and also commercial products that have a standards-based integration along with some registry and search capabilities to address these needs. The work was first focused on Terra.js, which is an open source geospatial framework, and then also the ArcGIS Online and ArcGIS Hub, which is another type of accessible cloud-based GIS environment that's obviously a commercial solution that I think a lot of us are probably familiar with. And then the one that I'll be able to talk about in more detail is actually our company called Voyager Search, where we built a solution for data registry and information retrieval called Voyager. The focus was really working with and embracing the wide range of data that is out there, and then along with the OGC standards that have been used to help catalog and make that content available. So as I mentioned, this work is really a summary of testing a lot of these different platforms and the various ways that we can connect to content. So when we looked at the type of data we are going to work with, it really is a wide range of disparate spatial and non-spatial data stores that are stored across structured and unstructured repositories. So if I've in my language, you can really divide the world up where there's a lot of people that have repositories of data, and those repositories could be stored on file systems or FTP servers. It could be stored in SharePoint. It might be stored in S3 storage from a variety of, let me see here, from a variety of different locations or from different cloud providers. It also is stored so it can, raw data can be stored as just repositories of content, and as we'll talk about a little bit, there's billions of dollars spent collecting this type of data. Unfortunately, there's also a lot of money spent on making that data available in catalogs. So, there are a lot of different catalogs exposing that data, which we'll talk about in a little bit. So our work was really to use to really look at all of this content, this whole corpus. So over the project, we were able to build registries of a couple 100 million data sources, applications, tools, services, and whatnot, all using a wide range of OGC and also other industry standards. The first project, we called it D100.1, and that's the Teria JS. And this is an open source framework for building geospatial catalogs that can then be explored. So the JS or Teria JS registry allows you to connect to and register a wide range of data sources that can then be searched and viewed and explored through a user interface. So focusing on a manual registration of content, but then having a nice map visualization and also some web processing capabilities to act on that type of data. We were able to use the Teria JS solution integrated with Voyager Search, where we found that Voyager Search could find content, but then also open it up inside of Teria JS. So we found some nice integration point, which we'll talk about. So here's another screenshot, and we have some GIFs of the workflow process. The next thing that we worked on was a D100.2, which was the ArcGIS Hub website. So again, Esri builds the ArcGIS Hub, and Hub is a great tool for, again, manually registering services where they can then be classified and categorized and then accessed. One of the things that we wanted to do is using it to map like very well-known spatial data infrastructures and create a registry of those well-known data sources to help decision makers find them. As you can see, they have a catalog and an interface here. The other thing that happened is that there's some integration with ArcGIS Hub that allows you to do some quick capture where you can install applications on your phone or other mobile devices, allowing you to install this app and then capture data quickly when you're in the field. So I think that this is probably a common need for emergency responders to be able to survey information, collect pictures, fill out a quick form, and then feed that information back where an emergency responder or decision maker can see the content. So as you can see a burnt down tree or a certain type of plant or something there. There's also now about a bunch of integration with OpenStreetMap as well. The next one, which I'll go into a little bit more detail since it's the area that we focused on, is using Voyager as a registry. And the focus I think, was quite interesting, is that one is embracing the fact that there's just a wealth of data out there, sometimes so much information that it becomes information overload and it can hinder progress rather than enhancing it. So we wanted to build a catalog, connecting to catalogs to build a registry of content. The other thing that we want to demonstrate here is that it's one thing to have a registry and be able to help with information retrieval to help you find something. But the other part is that we want to help make that data useful by running it through models that can help automate the process of connecting data with models to really generate insights, which we'll demonstrate and talk a little more about. And I think that's what's really important, is that that helps get information to decision makers even faster. So again, we wanted to focus on bringing data and models together in a way that makes the system very easy to use and access, and essentially bringing these tools to someone that really isn't familiar with geospatial content or even some of these powerful but complicated machine learning models. When you look at a system like this, we have a diagram here that really talks about the overall architecture. It helps to understand how it gets put together. So starting on the left-hand side, there's a framework for connecting to content. So this is where I mentioned that the system really embraces a wide range of places where you might store data, and you simply connect or use a wizard to say that a form that the interns use to point it to various repositories. So this was commercial content such as Planet, or government content such as Landsat, or a wide range of other catalogs that supported CCAN or DCAT, stack endpoints, or quite frankly, just crawling FTP servers and raw content. So you connect the content. The next step is you iterate over that content to extract information about each one of those items. And then the next step is you run it through a process for enriching the content. So you examine it. You can score it based on for fitness of use, but you can also automatically create new metadata or classify it and label it and find relationships, or if it's not geospatial, you can geotag it. So these are really just a menu of tools that you can assemble or add to a pipeline, and then as new content comes through the system, you use this to help enrich and condition the data. So all those are areas that the interns use to pull a wide range of content into a single registry to help it make more sense and be more approachable. The next area is information retrieval or search solution, where you can use textual or keyword search. You can view relationships between one content item and another. Also using spatial search and faceted search or filters, even using modern or common capabilities, like if you see a particular search result, then the system can generate relative content similar to it. So it can suggest more like this, or did you mean type of search results that help promote other content that you might not have known about but would be relevant to your area. And then obviously working with ontologies and taxonomies, even basic glossaries to form an overall lexicon. So that's building the overall registry. The next step, which we'll also demonstrate, is transforming and delivering data. So basically taking data and doing something as simple as opening it up in Terria or ArcGIS Hub, so open with those systems, or it could be a basic ETL type of solution to download the data to make it available to someone in the way that they want. But most importantly, and which we'll show a user interface for, is to take selected items in the registry and then add them to a list that then can be run through a model. So that's integrating content with models, and then lots of user interfaces, and obviously the system exposes itself as a wide range of OGC standards, including OpenSearch and Stack and CSW and WMS and all that jazz. The first step was really connecting to content. So you see this animated GIF. This is a mechanism to fill out a form, if you will, a dashboard to connect to a different type of content. So we're able to index over 190 million records of content into this registry over the course of 3 months or so, 3.5 months. We anticipate that there's over 100 billion things out there that we could easily connect to. And that becomes just an element of scalability and cost for building a cluster. And we were able to do that from national data sets to subnational and academic, commercial, and intergovernmental. So a wide range of content, including universities across 6 different continents, 60, 80 different countries, really whatnot. The next step was, as you connected to that content that I described earlier, there's an enrichment and conditioning step to adding value, to really understanding the essence of that data and helping bringing it out, but also helping to collate and fit a lot of different content in the same registry. So we're able to bring in content into a common lexicon for Earth observation, statistical, socioeconomic, environmental, and all kinds of other data. So we worked with a lot of ISO standards for metadata to conform a lot of data together, inject other metadata. Again, I want to mention one thing, that this system it's zero touch. So we're simply connecting to other systems and then building a more involved registry, preserving all of the original metadata, but then assembling it together with sprinkling on some other things on top to bring it together into a larger registry. So this is some stats: 190 million records in the registry, 66 countries, 80 different states. a bunch of different districts, cities, just really a lot. And as we started looking at some of the, especially some of the satellite imagery that's coming in, we're building 110 million or something records a day, just pulling things into the system. So it's quite scalable. I do want to provide let's say a thank you to AWS, who also provided an in-kind donation for infrastructure to help make that happen. The thing that I think is the last couple parts I want to make.
Yeah, well, I appreciate you filling in, and just wanted to give you a 1 minute warning just to wrap up, Brian, with the schedule.
Okay, thank you. So the last bit is that we were able to incorporate models into the system. So we looked at what type of decisions does a decision maker make, and how do we help understand the indicators that are required to help answer those questions. So we do have a fire damage assessment. Unfortunately, the Hawaii fires were happening around the same time we were working on this. So we're able to connect to live or real or near real-time satellite imagery based on the Hawaii fires. And then we were able to take footprints that we extracted from imagery from past satellites. We're able to add that data to a cart, a list, if you will, pick a model here, and then fill out a couple parameters for that model, but then execute a model on the fly to assess damaged building structures and so forth. So we could basically help a decision maker understand that, you know, we have billions of dollars worth of data that, you know, is being captured and made available. There's lots of different catalogs out there, but why is it so hard to just answer a simple question like how many buildings were damaged, how many areas where's the fire perimeter, how many acres were involved? So we're able to do that by taking the raw data we found. We took a building damage assessment model that Esri provided, and then we were able to automate the process of executing that model. So here's a live demonstration of this catalog, including a showcase of some of the content that we pulled in, and then that list of analysis-ready models that we were able to plug into the system. So you simply, you know, pick different types of models that you wanted to run. So and that's a lot in just a few minutes. So if you have any questions, please let us know. And we really want to thank everyone for allowing us to participate in this process.
Yeah, really appreciate it, Brian, and fantastic work. And also look forward to your presentation at Innovation Days coming up in December. All right, so I think that wraps up the discovery and access section. Are there any questions, or Josh, do you have any wrap up at this point that you'd like to add for this section?
I just did put some comments in the chat. Hopefully everybody got to see that. You know, we always, I think in these pilots and other activities, ask the question, well, you know, we know what's here, but how does anyone else find it? Because everybody who uses the internet realizes that finding stuff is complex, and particularly finding information. You know, it's easy to find content, to find keywords, but to find information and services and what's required to form knowledge and make decisions is not easy, and particularly in, you know, emergency situations. So we're very interested in that challenge, and what I think our participants have really shown is that there are a lot of elements to that challenge. It's you can have a metadata set and be able to search it, but can you search for what you need and not however that content happens to be characterized? And is it up to date? And is it comprehensive? Is it trustworthy? Does it give you access to authoritative sources of information? Can it tell you something about whether the information and services and capabilities that you discover are fit for the purposes that you have for them? And so going from, I can find a data set, I can find a service to utilize related to that data set, I can access an indicator or customize an indicator that really addresses my needs for awareness. That starts to become a very challenging, but a very worthwhile problem to try to solve. So we'll continue to have this aspect of all of the information sharing capabilities that are explored in these initiatives. And the next cycle of the disaster and climate pilots will be no different in that respect. I see that John is here, so I don't know if he wants to. Yes, I think he does like to talk something. So see if we can unmute you.
Hi.
We almost had you there. Try unmuting yourself again.
Can you hear me?
You're unmuted now.
Yes,
please.
yes.
Okay, yes. Apologize. So we've been having some technical difficulties. Basically, we've been trying to upload into the portal, and it just won't upload. I don't know what's going on. Right now, I mean, obviously, we just tried to upload only 30 minutes ago because we were trying to fix our video. It got all jumbled up. We worked late into the night last night on it, but unfortunately, yeah, Brian did a great job, and he definitely displayed everything that was going to be in the video. So hopefully, we can add it to the files, and it could be, viewed, later or by anyone if they feel like looking at it. So I just wanted to say that. That's all.
Yes, yeah, thank you for the update there, John. Sorry to hear about the complications, and there will be opportunity to share that in the portal, and then also on our YouTube channel with the other videos as well.
Okay, great, great, good. That's good. No, thanks, Trent.
Thank you.
Mm-hmm.
Is Leidner testing? Yes. Okay.
Yes, we can hear you.
Okay. Do you want me to just jump in, or are you ready?
Yes.
Do you want
yeah.
just a kind of intro?
I was just asking, do you want to share slides, or would you like me to share your slides for you?
Okay, I have my slides. Let's see what I have to do to get them up. That's you sharing them? I just assume
I'm
share
happy to
them
walk through them for you. Or you want to share them from your computer?
I want to share them from my own laptop, and are they being seen now?
Not yet. I just stopped sharing, so I'm going to make you presenter.
Oh, okay, that has to be done.
And then now you should be able to present.
Okay, show screen. Okay, how about now?
We can see it.
You can see it. Okay, so let me go to presentation mode, and greetings to everyone. This is Al Leidner, and I'm with the Gizmo team, and Gizmo is a geospatial information mapping organization in New York City. And we worked on Pilot 23 on a citizen science project. Big shout out to USGS and John Swanson and Sophia Liu, who really helped show us the way, and we've been following their progress for quite a while. And also shout out to Team Manitoba, who we work very closely with, which included Ryan Ahola, of course, from Natural Resources Canada, Mai Gajulis and Krista Olofsson. And the Gizmo team was Jin Wen, who's president of Gizmo, Theo Gottman from Basel Labs, Amy Ju, director on board of Gizmo, and myself. Just some quick picks. And the reason we're here is because we've always felt very strongly that as much as can be done, and believe me, I now know lots can be done with synthetic data and with satellite data and all the analytics. When it comes down to saving lives in a disaster, it's very personal, it's very one-to-one. And it means putting the responder in direct touch with the person who is in jeopardy, as Josh might say, with the right info, to the right people, in the right place at the right time. And that time is, and the place is constantly shifting and the time is changing in a disaster very quickly. So usually what you have in a disaster is chaos. Because there are so many people in need, and communications are often down, formal communications. 911 and 311 systems are totally overlaid almost instantaneously. What it's really calling for is a smartphone-based application in the hands of both responders and citizens to help augment 911, and that's the emergency location and language application we call Ella, and it was something that we developed again in collaboration with the Team Manitoba. You know, you might also think that this is the final mile of all the data that is being brilliantly created prior to a disaster. What we're trying to provide is that final mile of data that goes not just to the block, the census block or the census tract, but the exact location of where somebody in distress is located. As somebody who is caught in a building fire, they want the first responder to know exactly where they are, and they don't care about their personal information. They want their lives changed. And the responder wants to know exactly where he's looking for the potential victim, so he doesn't or she doesn't put their lives in any jeopardy. So, we see this smartphone capability as working in very close harmony with Earth observation data, and you know, the smartphone survey gives you the human intelligence that you need to actually then go in and save lives. One of the advantages of the smartphones, you probably know them, they enable rapid and repeated multimedia communications. They're like the Swiss Army knife of communications because so many things can be captured and transmitted through smartphones that it really provides you with enormous flexibility. And as the nature of a disaster is constantly changing with cascading effects and different events piling on, you need to have a tool in the hands of citizens and the response community that can react that quickly. A photograph from 3 hours ago is not going to do the job when the scene on the ground has changed utterly in the last 10 minutes. So we see even a building of a citizen, a family of citizen science tools to supplement 911 and support the response community and what could be millions of people in a disaster area who need to be attended to and listened to. So again, that smartphone, which is in the hands of billions of people right now, so it's a common technology, can manage repeated cycles of photos, sensor readings, questionnaires to provide persistent and precision situational awareness and trends over time for large groups of people, because that data coming in can all be automated. What are the constraints? I mean, this is not going to happen at the snap of a finger. It requires, most importantly, persistence of telecommunications, which often in a disaster go down. So that persistence could be in the form of aerial assets that enable communications, even if the landlines and land communications go down, or satellite. But that has to be built in for this to really be successful in a disaster and other conditions as well. That governed the design approach to Ella, and we developed a prototype application to test in New York City called Rat App, where we sent out the members of Gizmo with this application out into the field to spot rats and to capture information about them at the site, and then to transmit it back to a server wirelessly using smartphone capabilities. And we found that worked pretty well. It was not a production system, it was just a test system, but it worked pretty well. So we took that knowledge to Manitoba, the team Manitoba, the folks there that we were working with, who were in direct touch with their local citizens. And Team Manitoba shaped the questions that went into Ella, and Basil Labs and Theo Gottman, programmed that into the application, and listening very closely to Manitoba design considerations. So in this case, we were not building an application for emergency response, but to understand the business effects that drought has, and to capture that in a series of questions and captures, photo captures, and also voice recordings that those who were being questioned could enter into their smartphone. Also, compliance with Canadian protected A-level privacy standards, and so forth. Okay, so with that, I would like to introduce Theo. Theo, can you speak? Are you okay?
Yeah.
Okay.
Here, yeah.
Theo is our great programmer and creator, actually, of the platform, and he put together all the screens that he will now present to you. So go ahead, Theo.
All right, thanks, Al, and definitely a team effort here. So I'll just highlight right here on the login screen, not so much about the login, but the goal here, as Al was saying, is we want to be able to translate what's coming in, especially unstructured data or data sources that are not typically immediately mapped. So photos, voice responses, any language coming in, right? And being able to turn that into DRI data and ARD data, and then be able to immediately map that. So Al, if you want to go to the next screen here. So some of the things, yep, so this is the Manitoba survey that we were working on with the Manitoba team. Some of the components are very standard. So you'll have, all the main things that are needed. In the far left, you can see, title, description. You'll have multiple selects, text answers. And again, so this is really focusing on understanding the nuance of how is drought and impacting businesses and people's livelihoods, well-being. Next screen, please. So apart from the standard things that you'll see in other survey platforms, we want to focus on the voice input. And so we added a couple of things, small fixes and also updates during DP23. So one thing you'll notice is that we have time at the bottom. So we're always timing folks. Again, so any language that you speak into. We also added, so if you're clicking the, not just the voice, but you can also type it in for data concerns or data privacy concerns that any respondent has. Al, if you want to go to the next screen, please. some more numbers. We'll go to the next one. And then also photos. And so all of these, whether you're taking a photo or you are uploading multiple photos that you've already taken previously from your phone. And then finally, the thank you screen. Added a little thing here on this, in the bottom right, you can see that, to learn more, visit the website. This also works for entry screens, adding terms and conditions, especially if you're collecting any kind of sensitive data. You want users to be well informed before clicking into the survey. And then also at the end of the survey to be redirected. Next screen, please. So this is what it really comes to, is being able to take unstructured data and then being able to map those. And so in the top right, you can see topic classification. And so this is based on keyword binning. So you're taking keywords, and unclassified words are things that the AI is suggesting to you and prompting you to say, hey, please classify these. And so whenever new responses are coming in, if it's in French, for example, we translate it to English. And then we'll be using these keywords to put them in bins. And then all of this is mapped into the map. And so new responses are coming in live, being tagged. In the same way on the map, you can hover over any given dot and you'll be able to see photos, be able to see email addresses, phone numbers, all kinds of different questions. And so creating interrelation between the questions while you're quickly exploring them. And of course, all of this is also explorable via API if you want to bring it into your own platforms. Next screen, please. So with all that being said, potential direction here is to incorporate more sensors, right? So being able to get on the ground real-time information that's coming directly from the community, especially as folks are censoring up more and more. But being able to integrate these and then directly communicate that between first responders, folks on the ground, citizens, residents, and then of course the administrators who are in the command center. Next screen.
Okay, it's when I come back in.
Okay.
So
passing it back to you, Al.
Okay, thanks a lot. I just want to mention that there is a very obvious connection and synergy between these kind of tools that can be added to a smartphone and use a smartphone as a sending mechanism, and the health data that Ajay and Paul were talking about earlier, where you could actually be monitoring everybody in a community that is under extreme risk and be able to identify who's at greatest risk and then dispatch a nearest asset, a nearest response team to help that person. So this smartphone platform has enormous potential and capabilities that we should really start to explore. What did we learn about successful deployment of Ella? We know that the data has to come into all into one basic place within a community, either at a physical or virtual emergency operations center. And actually that this kind of dynamic needs to be worked into the National Incident Management System, that doctrine has to be created around this. It also must be part of an overall data management strategy at the EOC, and that would call for changes in the GeoConops that Homeland Security puts out, but really needs to reflect some of the modernizing of GIS capabilities that have gone on over the last 10 years. And it must be integrated into operational work process, the teams that are out in the field responding to an emergency, so that they can be put directly in touch with the public who is at risk on a one-by-one basis. It's what I call the responder-citizen synapse. It's where a responder and a citizen actually interact face-to-face, and the responder helps the citizen, either saves his life or brings the person to safety. And that is what this kind of a tool can do. And unfortunately, it's not what can be done from outer space. It's got to be done on the ground, face to face. And finally, next steps that we should be taking, well, increase the use of ELA type tools that supplement 911 and make the two-way exchange of information from responders to individual citizens and groups and types of citizens much more transparent and easy, so that you maximize communications effectiveness during the golden hours after a disaster hits, which is the time that you can save lives. And that's a very short window, a small window, and you need to have maximum communications during that time to make sure people are saved. You've got to fit Earth observation data streams into the EOC for preparedness response, so that that data coming in from the space platforms can inform the questions you want to ask via ELA to the public that is affected by the disaster. I would also give a little shout out to Pixelytics, whose guides I think become the foundation for a new GeoConops that everyone can use, that really tell the EOCs how they should be or how they can be using data if they want. And then a final, have to get my 2 cents in, create a testing lab demonstration center at a state or city emergency operations center to test all these interoperabilities between satellite data, aerial instruments, and smartphones and citizen science, to see how it all works together, because the only way you're going to know is if you actually try that out. And I know that the working together of federal, state, and local data is something that FGDC has been pointing to as a goal. We can add on to that the testing of the integration of all these different data types as an extra bonus for being able to bring federal, state, and local data together and integrated. So with that, thanks for listening, and look forward to the next phase of DP. So thanks a lot. Thanks a lot.
Thank you. Thank you very much. We are running a little bit over on time here, but do want to get through the presentation. So up next we have the guides that will be presented, and then we do have the Voyager video, which we could show after we conclude the guides. So let's, Andrew, would you like me to present?
Yes, please. If you could run through the slides, that'd be great.
Absolutely. All right.
Okay, thank you. Hi, everyone. I know I'm the last presentation, so I know you're all waiting to go. My name's Andrew Lavender. I'm from Pixelytics Limited, and we were the editors for the provider, user, and operational capacity guides for this disaster pilot. I say editors because the content was really provided by everybody you've been hearing talk today. So it's really important that their work sort of contributed to these. Next slide, please. There are 3 guides: an operational capacity, user, and provider guide. They are all standalone guides, but actually they work together. They support each other. And what I'm going to sort of talk you through now is how the operational capacity sort of sits underneath and where it fits in with the user and provider guides. The operational capacity guide is new for this particular disaster pilot, but the other 2 have built on guides from previous disaster work. So there's more than just Disaster Pilot 23 in here. Next slide, please. The operational capacity guide, the aim was to provide a document that gave disaster and emergency communities a sort of a roadmap of how to achieve geospatial readiness and how to put in place a strong and robust geospatial function for disaster response. So what we've done is we've developed a standalone document with the support of the Manitoba emergency team who've been working, who are May and Krista, who Alan mentioned, who helped us sort of focus what we were doing. And what we've developed is a capacity development framework, which outlines a set of incremental strategic actions across 6 themes. And it sort of gives a set of actions that each community can take forward from wherever their starting point is to develop or enhance their overall geospatial readiness. So if we have a look at that framework now in the next slide, please. So what we've got is we've got a vision, and we've put it up here as to establish the robust and efficient geospatial readiness across the disaster and emergency community, providing the capacity and capability to support disaster planning and response. Now that is just a vision we've put together, and we would say for any community who's looking to implement this, that it would be better if the vision was defined by them from where their starting point is now and what they want to achieve. So once we've got the vision, it's underpinned by 2 principles, data sharing and trust. And that is everything you've been hearing about today in terms of how we share data. But the trust is about sort of the trust of that data, the trust of the people, and the trust of the tools and the registries and the authorities of those data catalogues. And then underneath those principles, we've got a set of 6 themes that you can see outlined here, of which we've got strategic actions. And they're all sort of the key elements that we saw about what is needed. So if we move to the next slide, please. What you can see is for each of those themes, there are then a number of areas under each of those themes. So for geospatial skills, we've talked about identification of those skills, building geospatial relationships, and then developing data integration skills. And what we're looking at is sort of 3 levels: the individual people working with geospatial skills, the organizations with whom they work and what the organizational relationships are, and then the overall community environment in which they work. And so the skills and the strategic actions are looking at each of these levels. And you can see within each of the themes, there's 2 or 3 sort of areas. We move on to the next slide. We're going to look at geospatial data specifically, which here has foundation geospatial layers and disaster specific data layers. And as you can see, having gone from the theme to the area, under each one of these, there are now a set of the incremental strategic actions. So under the foundation geospatial layers, we've got 5 individual actions, which are about sort of developing the base maps. Whereas under the disaster specific data layers, there are 4 strategic actions. And you'll note that the last one is about reviewing the workflows developed within Disaster Pilot 2023. So if you move on to the next slide, please. What we've got, that takes us really to what the other 2 guides, the user guide and the provider guide. Now these 2 guides complement and mirror each other in terms of content. And what they really talk about is everything that you've been hearing about this afternoon. So under that, you can see the supportive tools, the registry services, the ELA reporting application we've just heard about, data visualization tools, and then the workflows about the drought and the wildland fires. And so those guides are giving all the details there. But at the bottom, you'll notice that there are also data sets related to flooding and landslides, which are from previous disaster pilot work. And so if we go on to the next slide, we'll talk about the 2 guides. The user guide, the aim of this is to provide a non-technical showcase. Now, there's been a lot of great presentations today. Some of them have been quite technical. So for certain parts of the emergency and disaster community, they might want to have a much less technical version of what it is. And this is what the user guide, this is the place to go. It's a plain, non-jargon, non-technical document that describes what issue each workflow or tool is looking to address, a non-technical description of how it works, the benefits it offers communities, together with all the collaborations that have been undertaken within the pilot. Again, some of the things we've been talking about today. And this sort of sets out a simple way of describing everything that you've heard about today. Now, of course, with the simple side, you also need the detailed technical side. And if we go on to the next slide, that's the provider guide. And for anybody who wants to be able to implement the tools and workflows that you've heard about today, this is the protocol that you need. It's a detailed technical document that describes everything that needs to be done to enable disaster and emergency communities to implement and operationalize the tools and workflows we've talked about. So this talks in detail about the input data, the processing, the outputs it produces, alongside the benefits and the collaborations that have been undertaken. So what we've ended up with is 3 guides. The first of which is the operational capacity, which sort of sets the scene and sort of gives you what you need to do. Then you've got the user and the provider guide, which essentially are focused on the workflows and tools that you've heard about all today. And that's what we're trying to do with the 2 guides. If you move on to the next slide, we can talk about where we see what's next, really. So for this, the operational capacity guide, as I said, this is the first time this has been produced, and we'd acknowledge that this is only the starting point. It's currently being reviewed by Manitoba to consider a potential implementation. And a bit like Alan said in his previous slide, also we need to discuss with FEMA about how this might sit alongside or work with GeoConops and the NIMS. We also want to sort of promote it wider to other disaster and emergency organisations and communities to get further feedback and improve it and improve the next phase. We've already had some suggestions of sort of how we could develop it in the next phase, sort of looking at things like producing templates or exemplars for some of the documents that we've got within here, or actually more sort of focus on what happens with an emergency or when an emergency or a disaster is declared. So that's kind of where we're looking to take the operational capacity guide. And if we move on to the final slide, the user and provider guides, I say these are very much driven by the participants in terms of the content that's there. But what we need sort of is to get communities to review them, to understand whether what they've got in there gives them the information that they need to be able to implement tools, or whether they need something more and what that might be. We also need to look about maintaining the persistent demonstrators that people have been starting to talk about, and how we're going to sort of try and develop that, because those are going to be what communities want to go and look at to understand how they're going to sort of take it forward. And then in terms of future elements, some of the things that we've picked up in terms of some of the conversations are we need to be looking at quick wins to sort of demonstrate the benefits of geospatial data to emergency and disaster communities. We will need to look at AI and machine learning in the workflows. Dean earlier talked about future forecasting, and we certainly need to bring more climate data into them to allow for planning. And then we need to think about how we can build on the work on the shoulders of OGC, sort of to develop a sort of overall ecosystem about how we can take this forward. These are the guides. They're currently going through review, and hopefully in the near future they'll be publicly available, and we'd love people to read it and give any feedback back to us. But that's everything from me. Thanks.
Thank you, Andrew, and great job throughout the pilot on pulling together all the information from each of the participants and organizing those into the guides. And what a wonderful resource for the communities, and hopefully we can assist with getting that into the hands of some other folks, as you mentioned there in the slides. So that concludes the planned presentations for today. We do have the Voyager video, which we did want to share with the group. So I can do that here. I have that local. While I'm pulling that up, we did have some time originally allocated for questions and answers. So while I'll pull that up, if you want to ask questions in the Q&A panel, or raise your hand as attendees, we can unmute you, and really appreciate everyone's participation today and hanging in there with us for these fantastic presentations. Josh, do you have any words while I bring up the video?
I usually have words. Are they the right words? Well, the right words at the right time in the right place. Yeah, so I really want to thank all of the attendees and remind people that it's a cooperative activity between OGC, the sponsors of the activity, and the participants. The participants have brought all of their capabilities and knowledge and their enthusiasm to solve these problems. So I really want to express my appreciation. And although I'm retired, this challenge isn't going away. So I look forward to the future iterations and associated activities that really work to get these collaborative and resilient capabilities out there where people are actually making use of them. As we said, we're taking technical approaches, but our challenge is to solve, social and organizational problems that stand in the way of everybody having the information they need to take the decisions that they must. So I don't know. We don't have a lot of time. It's overwhelming. Sure, the fire hose here, but the videos and recording of this session, this event, will be available. The guides should be publicly available sometime next month after a review process. And please get in touch with any of us who are involved in the pilot with questions and suggestions of what needs to happen next, or of offers to help, because it will take all of us to make these things a reality. And that's it.
Thank you, Josh. So with that, I'll share the Voyager and USGS GeoPathways video, and thanks again, everyone, for attending.
Complex and interconnected. Humanity is challenged with understanding and adjusting to ever-changing social, economic, and environmental factors as a result of a growing population, increase in disasters, extreme climate, among many other variables. Our future relies on a whole systems approach towards sustainable and innovative solutions built on reliable insights, information, knowledge, understanding, and informed decision-making. Over the last several years, humanity has experienced extreme weather events, some of the worst hurricanes, droughts, wildfires, and man-made disasters in recorded history. This year alone, NOAA declared that 2023 set a new record for billion-dollar disasters, exceeding $23 billion in damages. Coast to coast, the U.S. has experienced extreme drought, excessive rainfall, flooding, and wildfires. Similarly, the global community has experienced significant increase in frequency and magnitude of these events that have cost trillions in recovery. The ability to effectively share, use, and reuse geospatial information and applications in support of disaster response and resilience is dependent upon having a spatial data infrastructure already in place when disasters strike. Humanity needs innovative solutions, modern spatial data infrastructures, place-based understanding, and generative Earth insights and intelligence to respond to an increasingly uncertain future. Public and private sectors, academia, nonprofit organizations, and communities are working together with the Open Geospatial Consortium to create and share trusted data, knowledge, and technologies to improve resilience. Our aspiration in this pilot is to bridge the divide between stakeholders and providers of data and services to reduce loss of life and property, to improve preparedness and resilience in the face of an uncertain future. In this pilot, we demonstrate how advanced SDI architectures and interoperable standards help stakeholders and decision makers make new and beneficial perspectives into social, economic, and environmental issues related to climate and disasters. For this pilot, participants focused on research and engineering of advanced architectures, interoperable standards, and workflows that support registering of structured and unstructured data, data profiling, and spatial data enrichment to increase trust of data, models, and emerging GeoAI using W3C DCAT, ISO, and OGC standards. Collaborators engage transnational organizations and stakeholders throughout the community to understand requirements for geospatial framework datasets that address specific indicators and work broadly with local to global providers to mobilize high-value social, economic, environmental, and other data, services, and models to support the pilot. These trusted sources of data, models, and workflows were registered in the identified solutions and sourced to generate a wide range of products and services in the pilot. The team selected Teria.js, ArcGIS Hub, and Voyager Search, spatially enabled COTS, and open source platforms to establish an interoperable data mesh architecture that enables federation of local to global data, services, and workflows that can produce products and services. The first demonstration utilizes Teria.js. Teria.js offers registration, cataloging, mapping, analytics, and workflow capabilities in empowering stakeholders to search, view, and explore registries and catalogs of geographic tiles and services. The platform enables registration of content, URL-encoded parameters, map visualization, and workflows. Using indicators identified by stakeholders, collaborators developed a registry using Teria.js JSON coding requirements for DCAT and OGC data retrieval services. The graphic illustrates samples of the code, search in the registry, and mapping using OGC services that respond to fire and drought indicators. Mapping and analytics are showcased, addressing use cases related to communities at risk, open and participatory science, wildfire, drought, and health. Participants tested the ability to find and use SDI foundational data, topical and thematic data products to address public health threats related to changes in climate and natural hazards. Participants were asked to search content, map the resources, and build a story using environmental, drought, flood, and climate risk indicators from providers and health risk indicators from HSR developed during the pilot. Using Teria.js story feature, stakeholders utilize map services, workflows, and other content to understand the socioeconomic health, wildfire, drought vulnerabilities, potential climate mitigation, resulting from green infrastructure, and other insights and intelligence. Resilience coordinators and emergency responders require access to data that may include social, economic, and environmental variables, and specific documents and information to effectively plan for, respond to, and recover from disasters. The second demonstration utilizes ArcGIS Hub, which offers registration, cataloging, mapping, analytics, and workflow capabilities, empowering stakeholders to search, view, and explore registries and catalogs of geographic tiles and services. The collaborators worked to identify key resources identified by stakeholders through the ArcGIS online network, Esri Atlas, and many other open data sources, catalogs, and repositories. The team registered over 533 total resources through ArcGIS Online. The Hub registry supports the use of W3C DCAT standards to provide an open API endpoint for stakeholders to programmatically search and retrieve content. ArcGIS Hub supports various file formats for data and resources, allowing stakeholders to work with a wide range of content. The Hub also allows federation of open data groups within the ArcGIS ecosystem, and partners can provide access to group content that can be manually added. The collaborators investigated the potential to bulk register resources into the ecosystem, and the partner was able to demonstrate this capability in one of the collaborators' environments. Stakeholders highlighted the general need to address barriers to field-based data collection from participants. Participants in the pilot worked to demonstrate the ability to ingest data using geo-enabled mobile applications. Hikers, campers, forest rangers, and citizen scientists can help protect their favorite outdoor areas by collecting data to assess and mitigate fire threats. With billions of dollars spent collecting data and with much more spent to share and catalog data, why is it so hard to answer simple questions such as how many houses were damaged? Has there been any oil spilled in my area? Are changes in vegetation indicating a change in our mapped ecosystem? Stakeholders need trusted discoverable data to be able to efficiently find and use data. Data derived from many sources is needed to be resilient and responsive during a disaster event. Additionally, efficient access to models that can quickly synthesize large amounts of data is needed to timely deliver results. During a disaster, Various types of authoritative data are crucial for effective disaster response, management, and recovery. These data types provide valuable insights that can help authorities, organizations, and individuals make informed decisions and coordinate their efforts. Using new technologies to save lives, that's where Disaster Pilot 2023, registration, search, and discovery of data comes in. Bringing together disparate data involves the process of integrating or consolidating data from various sources that might be in different formats, structures, or locations. When coordinating emergency response efforts during a natural disaster, geospatial data must be fit for use to create accurate evacuation routes, assess the extent of damage, or identify vulnerable populations. The data's quality and timeliness are crucial factors, as outdated or inaccurate information can hinder response efforts and potentially endanger lives. The cornerstone of fit for use and fit for purpose is data profiling. Data profiling is an integral component offering a comprehensive analysis of data assets. It involves assessing data quality, structure, and content within a data set, model, workflow, or service, evaluating the authenticity, accuracy, and reliability. The collaborators utilize manual, algorithmic, and generative workflows to complete an initial assessment to determine fit for use and fit for purpose. The registry was engineered to support quality and validation checks utilizing ISO 19157 and ISO 1 redo paragraph. The cornerstone of fit for use and fit for purpose is data profiling. Data profiling is an integral component offering a comprehensive analysis of data assets. It involves assessing data quality, structure, and content within a data set, model, workflow, or service, evaluating the authenticity, accuracy, and reliability. The collaborators utilize manual, algorithmic, and generative workflows to complete an initial assessment to determine fit for use and fit for purpose. The registry was engineered to support quality and validation checks utilizing ISO 19157 and ISO 9001 standards pre-ingestion. The registry employs out-of-the-box and customizable templates and workflow processes that apply business rules based on regulatory, organizational, industry, and other content representation standards, roles, data classification, security, sensitivity, quality, and various other rules. Collaborators in the pilot also developed a lexicon and integrated the use of reference libraries into the registry engine to support consistent and efficient categorization and classification. The participants' registry employs a flexible search architecture that leverages open source technologies in the organic data science ecosystem, enabling collaborators and stakeholders to narrow down their search results and discover insights and intelligence by applying the following features. This hub features an intuitive search box, enabling users to conduct queries based on locations and specific facets. It offers a suite of filters to refine these searches further, ensuring greater precision in the results. Additionally, the system retains a history of past searches, providing users with convenient access to their previous queries for future referencing. The collaborators in the pilot validated use of current standards, tested data mesh federated architectures, new standards, developed integrated profiling workflow that leverages GeoAI deep learning for detection as a service. Voyager provides an integrated processing engine that accelerates the transformation of data to insights, knowledge, and intelligence. This pilot demonstrated these capabilities in the detection of oil spills, landslides, solar panels, buildings damage assessments, mangrove, solar, wind turbine detection, and storm tracking, as well as imagery related to flooding. On behalf of the GeoPathways, we would like to thank OGC, our federal advisors, and especially the participating partners who contributed to our research, development, and ultimate success in this project. And on behalf of our team, we offer a special thanks and gratitude to John Swanson, who served as our project manager and coordinator on this activity.
All right, and thank you for that the excellent video, and we will upload that to the portal as well. So that concludes our Disaster Pilot 2023 demo day. Thank you all for attending. Really appreciate it. Please stay tuned for the Climate and Disaster Resilience Pilot CFP, which will be coming out later this month. And please also join us if you can at OGC Innovation Days in DC at the American Red Cross headquarters on December 5th through the 7th. Thanks again and have a great day.
Thanks everybody for participating and presenting and attending. Talk to you all soon.
Well done. Thank you.
Thanks, everyone.
Thanks.
Thank you. Bye. Bye, everyone.
Appreciate the opportunity, Josh and Trent. Goodbye.